It is my pleasure to announce a seminar by Samir Mathur. He will tell us about contrasting the fuzzball and wormhole paradigm. Please, 1 hour. And maybe one technical announcement. Alexei, do you want to tell us something about regulation?
No, it's okay. Just
It's okay, okay.
it's okay.
Okay,
Just let's
okay.
people
Please,
talk.
Samir, yes.
Okay, thank you very much for the invitation to talk at this wonderful forum. I would like to share with you my thoughts on what is going on with black holes these days, and that's what my title here is about. So here is an outline of the talk. I will first briefly review the black hole information paradox, and then I will give you a very brief summary for the fuzzball paradigm, which I believe does provide a complete resolution of the paradox. I will then spend a little bit of time telling you the result of the small corrections theorem. And I think this is important because I think a lot of the confusions going on in the black hole field can be traced one way or the other to not fully absorbing the lessons of this theorem. And the lessons of this theorem really are that if you do not have the fuzzball paradigm, then to resolve the black hole puzzle, like to get unitarity, you either need non-locality, very long distance non-locality, and that's why I roughly call it like the wormhole paradigm, or you will have the remnants. Okay, so if you're okay with remnants, then that's fine, but you will have remnants, or you need extreme non-locality, if you don't have those, then you have to have a fuzzball. Okay. I'll then try to talk a little bit about my difficulty with some of the arguments which people have been making for what I have roughly called the wormhole paradigm. So I'll just tell you what my difficulties are. That may not be exactly a representation of what people would like to argue, but to what extent I understand the arguments. And then I'll, in the end up with a philosophical question. I think the differences that people are seeing between the fuzzball paradigm and the wormhole paradigm really goes back to what lesson we should draw from ADS-CFT duality. So I'll try to come back to the philosophy of where I think all these differences are stemming from. Okay, so let's begin with the black hole information paradox. So the paradox goes like this. You start with a star in some pure state, I'll call it psi initial, and that undergoes gravitational collapse. And so it becomes like this in the classical picture, all the mass has gone to the center. So in semi-classical gravity, you get this Schwarzschild metric. And the interesting thing about this metric, of course, is that for r greater than 2m, the space-like surface is t equal to constant, because this part is positive and this part is negative. But for r less than 2m, inside the horizon, a surface like r equal to constant is actually space-like. Okay. So the space and time interchange roles. And so then if you have to draw the space-like slices in this geometry, I have the radial coordinate in the horizontal axis here. So r equal to 0 is here, r equals 2m is here, and then this side is r equals infinity. And this you can think of as maybe Eddington-Finkelstein coordinate. Think of it roughly as a time. Then the space-like slices are time equal to constant outside, but they are more like r equal to constant inside. And so then you can see that the slicing of this geometry, a complete set of Cauchy slices, the slices are not identical to each other. The later slices, which you try to evolve later in the outside, but suppose you try to not evolve them closer to the singularity, so you never get into a domain of strong curvature, you can make these things called good slices. But the important thing about the good slices is they are not the same as each other. In fact, there is a stretching of the slices. You keep having this stretching, and that's what leads to particle production. So if you have some wave mode here, on a later slice, when it gets stretched, the wave mode gets distorted, and that produces a pair of entangled quantum, one outside and one inside. This was basically Hawking's calculation. The other thing we notice from this picture is that this line here, the space-like slice here inside the horizon, is r equal to constant. And because it is r equal to constant, it can be infinitely long. So there's an infinite amount of space inside the horizon. So one way or the other, all the issues with the black hole will come down to these issues. Firstly, because there's so much space inside the horizon, you can store a lot of information. And that's how the entropy inside the black hole can become more than the Bekenstein entropy. So that's where the puzzle comes from. And why do we create particles in the first place? And again, if you have a space-like part like this here and time like here, the whole thing is space-like. So if you have a space-like slice like this, which is t equal to constant here, but r equal to constant here, there's no way to get a time-independent slicing. So geometry can never stabilize. It keeps producing particles. So then this is just we just extract the essence of the Hawking puzzle right here. And so you can see what is happening is the initial matter which fell in to make the hole, let's just say it's over here. And then after some time, you create one pair of particles. Then that inner member of the pair moves out. The outer member moves further out. And then in the space in between, there is more stretching. And you create another entangled pair and so on. So the entanglement entropy, let's say, of the pairs on some initial slice, let's say, was equal to 0. We are computing the entanglement of what is outside with what is inside. Then on this slice, in this toy model I have taken, so in a toy model, we can just say that there are just two states for each of these. And so you can write the state as for this B1 and C1 is 0, 0 plus 1, 1. Okay, so the total state on the space-like slice is the state of the matter, and then the state of this slice, and then the state of this next pair. There are two pairs and so on. That's what you get schematically in the leading order Hawking computation. So you can see the entanglement of the outside with the inside was 0, then log 2, then 2 log 2. So it just keeps growing. And that is what will lead to the information paradox. So now if you look at the emission steps over here and the entanglement over here, you see it is linearly rising. And so it's not like the behavior for a normal body where entanglement at first may rise, but later on it's going to come down and go to 0 when the object actually evaporates. So with the black hole, because it keeps rising, once you go near the end point of evaporation, there is a sharp puzzle. And so what is the puzzle? If the black hole evaporates away completely, then whatever is left, it is entangled, but there's nothing it's entangled with. And there's no way to write a state for that. You only get a density matrix. And that's the loss of unitarity that Hawking proposed in 1975. But then if you say we don't want to have that loss of unitarity, you can say the evaporation stops when the whole thing becomes, let's say, Planck size. So you have a Planck remnant, but then this remnant has an entanglement n log 2, where n was the number of emissions. But because we could have started with a black hole of arbitrary size, we then have to argue that this Planck size remnant can hold an unbounded number of states, as many states as we need. And then you can have worries about how to make a model where in a small volume with a small mass, like just Planck mass, how you can hold an unbounded number of states. So either of these possibilities becomes a little troublesome, and that's the information paradox. There are alternate versions of this problem, which are basically similar, but they are also going to be interesting for us to note. You can, for example, not let the black hole evaporate, but keep feeding it at the same rate at which it is evaporating. So then the negative energy partners, the members that came out, the green dots, and the negative energy partners, the red dots, they are still there as before. But there are also these positive energy quanta, the blue dots, which I have started throwing in. So the black hole always maintains a mass m, but because I can keep doing this for as long as I want, the entropy of entanglement, I can make it to be much bigger than the Beckstein entropy. So then again, if somebody said that the entropy of the hole is given by the Beckstein entropy A over 4G, then how can you entangle by more than A over 4G? So same puzzle, but just a different way of stating it. Another way of saying it is this bags of gold problem. You don't even have to look at any Hawking evaporation. Just start with this space-like slice as a given slice. It's a smooth slice. So just start with that as an initial condition. And on that, you can put these negative energy pairs, partners, negative energy quanta, and the positive energy quanta. They're all long wavelength quanta, let's say a kilometer each or something. Radius of the horizon, think of as 3 kilometers for a solar mass hole. And then these quanta are separated by a few kilometers, and their wavelengths are like a kilometer. So nothing bad happening anywhere. But because they are alternatively positive and negative energy, the amount of mass I can store here, amount of entropy I can store here is infinite. So log of number of states can be made much more than S Bekenstein. And then suppose somebody tries to say, no, something is wrong. You can't actually make a slice very long because I have to make the slice long to store that much entropy. Well, it's not so easy to just make a conjecture like that. You can't just say that, because the problem is if you look at this part of the geometry, this long slice, you remember this is space-like and time is like going like this. The metric there is just like the metric of a universe. I've just drawn it horizontally here just to make it the way normal space-like slices look. And this is the time direction, this direction over here. It just looks like a cosmology, asymmetric cosmology. So it's homogeneous but not isotropic, heading towards the big crunch. This is the big crunch. So in our cosmology, we know at least we believe, we can make a space-like slice of infinite extent. That's the model of the flat cosmology. And this is conceptually the same. So you can't just say, I don't want to have such slices, because you can start with such a slice. Okay, so if you don't allow this, then you won't have to allow the cosmology. So there are no easy answers to the puzzle. So anyway, one way or the other, we are getting into some trouble, because once you have a horizon, then inside you have this very long slice. And with the very long slice, you have positive and negative energy quanta both inside, because space and time have interchanged roles. And then you get into the black hole puzzle. Okay, so what's the solution to this puzzle? So I think the answer is given by this so-called fuzzball paradigm, and many people have worked on it. I have tried to list some of the names of the people here who have contributed papers, but there are many others whom I may not have listed here. I will not actually talk about any technical details of fuzzballs. I will just try to give you a rough impression of what the idea is. And if anybody is interested in the technical details of fuzzballs, we can have a different conversation on the side. So the whole idea is this: in string theory, there are no free parameters. The string theory is just one theory. There's no free parameter. You can, of course, take different compactifications, but the basic theory has no choice in which strings and which branes are the matter content, or what are the interactions between them. That way, there are no free parameters. So if you have to make a black hole, you have to do it by taking a bound state of strings and branes. Okay? So let's go ahead and do that. Let's make a bound state of strings and branes. And then you find that the size of the bound state, at weak coupling, you might think you just take some strings and branes, you make a bound state. You might think the size of the bound state is Planck length or string length, but of course that may not be interesting, because you're at weak coupling, you're not actually looking at a black hole. So let's increase the coupling. When you increase the coupling, the mental picture might be that all these strings and branes will somehow go to the center, again make some kind of a mess of Planck size or string size, and then a big horizon around it, let's say 3 kilometers radius, will develop, and all this region will be the vacuum. But that's not what we found. What happens is, if you try to estimate the size of a bound state of strings and branes in string theory, you find the size of the bound state actually grows with the number of branes which are inside the bound state. It also grows with the string coupling G. And so if you take the D1, D5P black hole, which was laid down by Strominger and Waffa, and you estimate the size of the bound state at coupling G, then you find the size of the bound state is given by this kind of an expression. We don't need to know the details of the expression, because I'm just being schematic on what came out of those computations. You can see the computations here. But N1, N5, Np are the numbers of the different branes I have, different charges I have. G is the string coupling, alpha prime gives the string tension. V and L are volumes of various compact dimensions in this compactification. This is the volume of a T4, this is the volume of an S1. And what you find is, for all charges and all values of the coupling, this expression is of the same order as the horizon radius you would get for a black hole with those charges and at that value of the coupling and those compactifications. So it's just an observation. If you try to estimate the size of the bound states, you find the bound state size is always of the order of horizon size. And so that gave the idea that perhaps in string theory, you never shrink to inside your horizon. You never end up making something like this. And so perhaps there is no black hole. And as such, in this little picture, this is whatever you have in place of a black hole. And that's what is called a fuzzball. So then, well, this was just an estimate. But after that, you have to go and actually make these solutions one by one. And that's the whole fuzzball construction that has been going on for over 2 decades. We take the strings, theories of states in string theory one by one, some branes, some momentum charge, some strings, and so on. You make a bound state. And then you actually explicitly try to make that bound state and look at it wave functional, look at the construction and see, do you have a horizon like this one? Or do you just get something which is more like a star or a planet, that there's no horizon? And so many cases have been constructed. You can construct all states which are what's called the 2-charge extremal hole, the simplest hole. Many families of 3 and 4-charge states, can make some non-extremal states, can compute radiation from those states. So a lot of this stuff has been done. I'll give a rough summary sort of in my concluding slides of all the things that have been done. But in each case that has been tried, you find you never get a horizon. You just end up getting what we call a fuzzball. You just get something which is morally just like a star or a planet. And so that gives rise to the fuzzball conjecture that no microstate in string theory will actually have a traditional horizon which produces this kind of entangled pairs at leading order. There can always be small corrections, because even the traditional picture, we take this as the leading semi-classical approximation. So because there can always be small quantum gravity corrections, I always write plus order epsilon to whatever the Hawking's leading order answer is. But no, we are saying that's not the case. There's a complete change at the horizon. It's just like a piece of coal. And the whole problem, of course, with that piece of coal was you want the black hole to be like a piece of coal, because then there will be no puzzle. But the problem is the no-hair theorems always told you nothing can be supported here as a structure. Everything has to go to the center. But now we are finding that's not the case. You actually have a complete set of hair for all the cases you try to make. And you, in fact, get something which is indeed more like a planet. So how do we bypass all these no-hair theorems? And you can see this nice paper of Gibbons and Warner from 2013. You find there are special features of string theory, which involve having extra dimensions, extended objects, or Chern-Simons terms. And each of the no-hair theorems that people proved in the past, in each of them, you can find one or the other condition is violated because of the special features that you actually get from string theory. But even so, though you can see this technically, what about the rough intuition that if something becomes close to the horizon size, the gravity is so strong, it will suck it in? That's the rough intuition we have. So for example, there's something called the Buchdahl theorem. If you take a fluid sphere with pressure, which is monotonically decreasing outwards, if you make its radius smaller than 2¼ m, then if you try to integrate the pressure balance equation, dP by dr is equal to the force, gravitational force, you put the pressure to 0 here, you integrate inwards, the pressure is rising. If the the radius of the ball was less than 2¼ m, the pressure hits infinity before you reach the center. Okay, so then you say this is bad, it must collapse. So once the fluid sphere actually becomes less than 2¼ m, it must become a black hole. So those are just, you can of course say string theory doesn't give you a perfect fluid, so why worry about it? But morally, the fact that once you make something very close to the horizon, the pressure on it to get sucked in is very large, that is still there. So let's see, let me give you a toy model for how that actually works out if you look at these fuzzball constructions. So let's take a toy model. Suppose you take the geometry of Euclidean Schwarzschild. So you know that this is the metric of Euclidean Schwarzschild. These last 4 terms, I've taken t to I tau. So this is a Euclidean geometry, these 4 guys, and they make you like a shape of a cigar. The cigar closes off at r equals r0. This is a compact circle. So this direction tau is made periodic like this. Okay. So this is a cigar, but I'm adding on a 5th dimension, the times. There is the time. This is not a Euclidean geometry. It's a Lorentzian solution, but just look at this particular Lorentzian solution. So what structure does it have? There is a hole cut out of space here. There's nothing in there. Space ends here. And the compact dimension, you come here and it smoothly caps off. Okay, so in all directions, it just comes and smoothly caps off. It's a solution of the vacuum Einstein equations. So you can dimensionally reduce on this tau direction, this compact circle. And then it looks like you have a 3+1 gravity solution. And the size of the compact circle, because it's changing, you have a scalar field. The size of the compact circle gives you a scalar field. And then it looks like you have a scalar field with some scalar field gradients. The scalar field has a normal stress tensor, just dimensional reduction. And then you can say, look, I have a scalar field here from the 3+1 dimensional point of view. It has some gradients, so it has some energy, it has some stress tensor satisfying the normal positivity conditions. Why isn't this scalar field just collapsing? If you work on a stress tensor, you find that the stress tensor components are actually diverging as you get close to here. And so again, you can start wondering, why is something not singular happening? Why is the thing not collapsing? And you find that the pressure is actually diverging here, as I said. So it's like the Buchdahl theorem. Buchdahl would say, hey, at this point, something has gone wrong, throw away this solution. But of course, there's nothing wrong with the solution. The whole point is a completely smooth solution in 4+1. It's just that if you try to dimensionally reduce it, 3+1 and a compact circle, the reduction goes bad. Okay? So there's no horizon, nothing, but GGT never changes sign in this. But as a 5D solution is completely smooth and regular, in fact, it's a solution of vacuum Einstein equations, but its reduction to 3+1 is what doesn't work. And so morally, that's basically what we see in all these fuzzball constructions. Outside, you have normal space-time, but once you get inside this region, which is of order 2m plus a few Planck lengths, the compact directions are no longer trivially tensored with the non-compact ones. Okay, so you get a structure where, like in the case I just showed you, the compact direction just shrank to a point. So you get lots of structures here like Kaluza-Klein monopoles, anti-monopoles. There are S2s between them. There are fluxes on the S2s. You can put strings on these fields. So there's all kinds of structures there, but there are a large number of these structures where the compact dimensions are not trivially tensored into the non-compact ones. So as seen as 3+1 dimensional solutions plus matter, they will all look singular because the dimensional reduction goes bad. But as solutions of 10D, they are actually all completely fine. And so these different structures, we would like to then say, give the different microstates of the black hole. But then the point is that if you go look near the horizon, the state there is not like the vacuum. Its overlap with the vacuum is tiny. It's not like in the semi-classical black hole where the overlap with the vacuum 1 will be almost 1. You would say 1 minus epsilon. But here the overlap with the vacuum is basically 0, very small. There's no pair production, even including small corrections. There's just nothing like that. It radiates like a piece of coal, and the whole entanglement just then comes down, just the way it would for a piece of coal. So given this,
can I ask a question?
Yes, please.
Yeah. So I would like just to have a confirmation. So in full, let's say in string theory, is the existence of fuzzball microstate geometry like a conjecture, or there are like really solution which go beyond the toy models and tells that for sure there will be these fuzzball basically solutions? Because you mentioned
Good
that it's a
question. No,
conjecture.
it's not a conjecture. So that's what people have been doing for the last couple of decades. Maybe I can just jump out to a slide which I have for near the conclusion part. No, I can't see these slides. So let me see if I can get to my. Can you still see the screen? I'm still sharing.
Yes.
Okay. So let me see if I can show you something to better answer your question. I had a slide there showing roughly the kind of things that we have that actually go into the construction of the. So let me show you this slide.
Mm-hmm.
Okay, so the idea structure, the situation is roughly like what happened with M theory. We take all the various limits of M theory. We can see 2A, heterotic, and so on. We normally draw them at the vertices of a diagram, and inside we say it's something messy, but we believe the theory exists. So there are so many constructions. In the Strominger-Waffe thing, if you want extremal and the near extremal and non-extremal holes, you have some kind of a model where you have some D5 branes, which are given in green here, like sheets. There's some D1 branes, there's some momentum modes. So all arbitrary ways of winding these strings in different ways and putting momentum, anti-momentum modes, they give you all the black hole states. Okay, so morally we know if we can count them all like that. Then you take various special cases, like you take all the ones which have, let's say, no momentum, only 2 charges. And the duals of those can be explicitly constructed. So you know all of them. Then let's say you take all these circles to be in the untwisted sector, all with the same spin, but you put 1 unit of momentum on one of them. So we know the geometry for that. It's one limit because only one excitation of momentum. But then you can put the momentum on all of them, the same momentum. That's the other limit. And so this one you can also get. So this one comes out to be a classical smooth geometry. This looks like one quantum placed in a geometry. If you put it on some of them and not the others, it's just messy. So the 2 limits are, this is like one photon in this room, which you can study very easily by quantum mechanics. This is like a coherent state of photons, which you can study by classical electromagnetism. Mm-hmm. Anything in between is just messy, but it's still there. So then you can have things where you have one string inside there. Then you have things which give you a condensate of strings, but then that again turns to a classical geometry. You can do some non-extremal things, but those are over-rotating. There's something called superstrata. So all different kinds of limits. Somewhere you are putting both momentum and anti-momentum. Sometimes you're having a high twist. Sometimes the duals are stringy. So all possible corners of this you cover, but they're all extremal in some way. Like you can do completely neutral, but very fast rotating. Okay. You can do some neutral and non-rotating, but then for those we don't have a CFT identification. So a large number of people have doing all kinds of things. And then you can say, okay, what about the middle? All the extreme, all the limits where you have, maybe only one excitation or they're all excited, they have been covered. And then what I'm going to talk about is that if you say that, okay, but the more messy ones, they all might be black holes, then you have this small correction theorem, which will tell you if they are not fuzzballs, if there's even one guy which is not a fuzzball, then the theory will either have to have non-locality or remnants or non-unitarity. So it's a small correction theorem that really finally, I think, clinches the deal for me. All these things told us what the states roughly look like. So we know so much about it from all these constructions. But then if somebody says, no, there's a whole more complicated ones which actually have a smooth horizon, the small correction theorem tells you no, because if you have even one state like that, you have to choose between these 3. And I think we don't see any evidence for these. That's why I think everything is basically like a fuzzball. So let me just go back to where I was, and I'm glad you asked that question now, because I was anyway going to mention what fuzzballs have been doing recently near the end. So we just talked about it now.
Can I ask a related question?
Yes, please.
One question. So actually, I heard from Kellogg Steller that in heterotic string theory, in some limit, reduces to the quadratic gravity in some low energy limit. And Steller has studied recently spherically symmetric solutions in quadratic gravity, which is already very hard task to do. I mean, you need to go and solve numerically to get all the solutions. Yes. Now you're saying string theory, I believe it's much more complicated than stellar gravity.
Yes.
And then how do you actually obtain solutions? I mean, I'm really puzzled.
So it's very interesting. What happens is that normally you would think if you go to strong coupling in string theory, you can't do anything. So that's why people were counting the states of string theory at weak coupling all the time, right? But at strong coupling, they said, we don't know what happens. But it turns out there is a different expansion parameter. Let me call it quote unquote expansion parameter, which is how complicated the state is. So like in that picture I was showing you, suppose you take lots of strings, but put them in the same state. You make a condensate of strings in the same state, or a condensate of gravitons all in the same state. Then it actually again becomes classical. So what is happening is that if you make a condensate of anything, it again behaves like a classical thing is what we are seeing. Just like if you take photons in this room, if you have a black body, thing is it's very messy. Nobody actually writes down a state of black body radiation because it's so messy. So that you would write a 1 photon in the room, 2 photons in the room. But if you put lots of photons in the same state, you get a laser beam. Now the fluctuations are 1 by n. It's almost given by a classical geometry. And those are the guys we have been able to find. So you don't have to go to weak coupling, but you can go to states which are quote unquote simple because they have many quanta in the same mode. So you start with all quanta being in one mode, you can find it. Then you put half the quanta in one mode, half in another mode, slightly more complicated. It's like a laser beam where half the energy is in one harmonic, half the energy in the other harmonic. You can write that down also in terms of classical modes. So you do the limit of a few strings on one side and a condensate of strings on the other side. And once you caught both the limits, you say, okay, I think I understand what's going on.
Okay, so I mean, if I understand correctly, so the fuzzball is completely quantum description. It's not about, I mean, solving classically the solutions. I mean, am I correct?
So that's what I was saying. Just like with photons, if you have 1 or 2 photons, you have to solve it with quantum mechanics, write the wave function. And so when we have one graviton or one string or few strings in the bulk, we write down that. And when we put a lot of strings or gravitons in the same mode, it becomes classical. And somehow, even though the whole theory is quantum, talking about the full quantum gravity, you can describe the thing quite well by just using supergravity. But you have to use all of supergravity. All the dimensions, compact dimensions matter, the fluxes, everything has to be completely perfect. If you make a mistake, even in some coupling constant, the solution becomes singular or gets a closed time-like curve. But when you do everything properly, with the correct numbers of string theory, you always get a fuzzball. No closed time-like curves, no instability, nothing.
Okay, thank you.
Samir, sorry to interrupt you again. There was a question in the chat by Robert Brandenberg. I don't know, Robert, if you want to ask the question.
Okay, please go ahead.
Yes, I mean, my question is, if the fuzzballs reach to the horizon, then the density of the fuzzballs has to decrease as the mass increases. And is there a way to see how this arises?
Yes, so what you're asking is, what is the internal structure of the fuzzball? Can we describe it by a local density? So I am actually not sure I understand the answer to how to describe it in terms of a density. So I'll just back up a little one step from your question, because the idea of a density makes sense as long as I can first lay down a background space-time, and on that I say, okay, there are things here, right? But what is happening is that this space-time, let's take a toy model for what is happening in all of these places, and let's assume these are all little bubbles of nothing kind of thing, topology, and there are many bubbles of nothing all puncturing my space. But now there is no background space there on which I can really say what is the density. So somehow I've not been able to phrase the question in that way for myself. In the simplest cases, when you actually, in the two-charge extremal, when you can write down the states explicitly, yes, you just have a string sort of moving around in some way, and there it is true, the density is lower as you go to the larger numbers. Absolutely, there it is true. For the more general cases, I have not been able to understand it that way.
Thanks a lot.
Okay, so let's go to the small corrections theorem, because I think one way or the other, all the issues that I'm seeing with people. So again, the end of what we were here was, I was just saying here that to me, it seems the puzzle is over, has been over for a long time. Why are people still worrying about the information paradox? What is there to say after it now? String theory seems to be very clever. If I don't have all the things of string theory, like the compact dimensional strings and all that, I can't make the fuzzballs. And then, as we will see from the small correction theorem, you will lose unitarity, or you will have remnants. There is really no choice. But with string theory, the string theory seems to be clever enough to find its own way out. It just makes these fuzzballs instead. So it seems the puzzle is nicely solved by string theory automatically. So why are we still worrying about the information puzzle? And I think all these worries go back to one way or the other to this thing which I'm going to call the small corrections theorem. It will essentially tell you that if you don't want to have a fuzzball, you say, no, I don't want to corrupt the horizon that much. I still want some kind of rough semi-classical picture to emerge on the horizon. Then you must choose between one of these three possibilities, either extreme non-locality, like non-locality from the black hole, not just up to 3m or 4m, but all the way up to m cube where the radiation is sitting. Okay, that's the non-locality. Or you have to get remnants, or you have to have non-unitarity. People may be okay with remnants, but then they have their own issues, which we can talk about separately. So to just convey to you what the small correction theorem says in the context that we are going to be talking about, let us look at a scenario of how people sometimes think about the quantum gravity of black holes, which is very tempting, but which does not work. Okay, so just focus on, in the end, I'm going to say it doesn't help you, but this is the picture at the back of the mind for many people. So many people say, let the exact description of the black hole not be the semi-classical geometry that Hawking took. Let's agree it is some very complicated quantum gravity mess which is going on in that region. So let's say all the way up to r equals 4m, some quantum gravity mess is going on. All we assume is the dynamics in that region is unitary. So whenever I'm talking about the exact theory, maybe the whole string theory put into a computer, I'll try to draw it in black. Okay, so there it's in black. And we will not try to specify anything about it. Of course, far from the whole, let's say r bigger than 100m, like I go far out. Again, the exact dynamics, which I always write in black, is given by standard quantization of string theory around flat spacetime. So there's no funny non-local effect or anything I've put in here. I'm just saying if you go really far from the whole, 100m or whatever size you want to choose, you can then open up your favorite textbook on string theory and you just get a normal physics of gravitons and strings here. Okay. Step C. However, suppose I also want that some complicated combination of these quantum degrees of freedom, these quantum gravity degrees of freedom, reproduce for me an effective semi-classical description around the horizon. This is where, if you want that, that's where all the issues are going to come from. So some complicated combination of these exact degrees of freedom, they yield effective semi-classical quanta. Let's say those are described by a scalar field, which you can expand in this way in curved space the way you do. And so these degrees of freedom give this, these degrees of freedom give this. And so I've just drawn that for you.
Samir, what exactly the definition of non-locality in this context? I mean, what kind of
non-locality? So that I will come and tell you.
Okay.
Give me a second, I will come and tell you. So by the way, note that in this region, anything can be non-local. Something can be from here and mean something here. Like here, I'm just writing things at random. We're not saying anything about this region.
Yeah, but my question is related to kind of in string field theory. In string field theory, there is some kind of non-locality which appears in the vertex interactions of the strings.
Okay, so we are not talking of non-locality over distances of order string length. We are talking about non-locality. When I say non-locality, I mean distances where the energies of the particles involved are low, like the normal quanta in the lab, but the non-local effects are across distances which are the size of the universe. Huge. So that's the m cube. The radiation, by the time the black hole evaporates or halfway evaporates, the radiation goes to a distance, horizon radius times m over m Planck squared. So that's trillions of miles, right? So non-locality from inside the black hole, a Hamiltonian which is going to interact with things that far and change them by order 1. That's what I mean by non-locality.
Okay.
So right now, that's not here. Right now, anything I do here, this is all fine. And so then with this effective scalar field theory, you'll have vacuum modes and they'll evolve to pair creation. That I can't help. That's just the Hawking's original calculation. So you're forced to get the creation of entangled pairs in this effective description. Effective is everything I draw in red. And I'm going to be very generous about it. We are going to ask this effective field theory. This effective field should work only for long wavelengths, let's say longer than 1 Fermi. We understand physics down to nuclear scales and bigger scales like meters, kilometers, down to a Fermi. I'm not asking anything near the Planck scale. So the effective field theory only has to work at 1 Fermi and above, where we have checked everything in the lab. And the dynamics of the effective field, box phi equals 0, it doesn't even have to be reproduced exactly, down to some accuracy epsilon, which is much less than 1, let's say 1%. So it doesn't even have to be exact. We don't even assume that this map to the effective degrees of freedom works for all times. It just has to work in a space-time region where I can produce a few pairs. Okay, because I have to produce a few pairs. If I can't produce, that's just a region of size m, 3m, something like that, a few kilometers. Otherwise, I can't even talk about the Hawking puzzle, right? So that's what semi-classical means. I can evolve, let's say, a few pairs. After that, I may have to rechange the description of how I define the effective degrees of freedom from the complicated mess. So even that I have given. Okay, under these very general conditions, let's see what happens. Now with the following, you have no choice. In the exact picture, which has been put into a computer, some messy combination of these becomes the quanta which will be radiated, and that messy blob is heading out. In the effective semi-classical picture, I'm getting these entangled pairs, which are like scalar field quanta, which up to some corrections are heading out. So up to here, I have no choice. And as the following evolution also, I have no choice. This guy sort of goes out, let's say, past 100 m, and at that point, I've described it in terms of normal gravitons and strings, because there I've assumed it's just normal flat space physics. And this quanta also, when it goes out, at infinity, there's only one physics. There's no effective physics. Effective is exact. So it's again made of the strings and gravitons, except that because I was always allowing order epsilon errors in the semi-classical description, what I get in this exact description, what I get my approximate description, they can differ by order epsilon. Okay, so all this looks like something that anybody doing string theory would like to have. And it is something that many people have at the back of their minds. The problem is that with all this, the small correction theorem tells you that under these assumptions, the entanglement graph of the exact quantum gravity theory will keep rising. It's not going to come down the way you want the page curve. It's also rising the semi-classical theory. The pairs, of course, coming up in semi-classical, but that, of course, you expect, because people say semi-classical is increasing because Hawking took semi-classical. But there's always been this belief in the minds of people doing a lot of these things these days, that somehow the exact quantum gravity theory is clever and makes the page curve come down, and the semi-classical approximation is the one which shows it going up. So what we have tried to do here is say, what do you need to do to actually make the page curve come down in the exact theory? And if you just do everything within Forum, you make it as non-local as you want, as quantum as you want, it does not help you. Okay, so this is why the small correction theorem is important. It's not an obvious theorem because it uses the strong subentropy inequality of quantum entanglement entropy of quantum information theory. And that's a very non-trivial thing to prove. But of course, we're not proving it, we're just using it. And if you use this in about one page, you can actually prove this, that the entanglement of step n plus 1 will be equal to entanglement of step n plus log 2. It goes, that's for the leading order of Hawking answer, increased by log 2 at each step. But if the correction at each step is only by order epsilon, the semi-classical approximation works to order epsilon, you can at most decrease this by 2 epsilon. You cannot just keep on saying that, oh, because I'm emitting so many quanta, there's some delicate correlation, something happens between them, and in the end, the page curve comes down. So the whole beauty of this, just one second, the whole beauty of the strong subentropy inequality is that it doesn't depend on the number of quanta which are being emitted. You can't trade the smallness of epsilon with the largeness of n. So the thing going on the back of people's minds was often that epsilon may be just 1%, some error, but the number n of quanta might be 1 million. So somehow in between them, the F errors could accumulate and somehow the page curve really comes down. But you can't do that. If each pair has a correction of only epsilon, because that happens because you want a smooth horizon, what happens at the endpoint also cannot help you, because at the endpoint, this problem is you're already in the mess, right? So there is no way to get out of it if you maintain the semi-classical approximation with these assumptions. Let me take a question. Somebody had a question?
Yes, just about your assumption. So
yes.
If I understood well, this theorem is based on, there are 2 points which are, I think, important that can be also discussed.
Yes.
One, you start from scalar field theory, and I would be curious what happens in case of fermions, because that kind of entanglement curve that you showed that starts from 0, reaches maximum and go down is typical for fermionic systems. And the second is you assume the validity of string theory, but if string theory is not valid or doesn't work, the theorem rules out, I think.
Okay, yeah, thanks for that question. So that's very important to state. So when I was talking about the fuzzballs, that works only with string theory. If you change string theory, you're not going to get fuzzballs. For example, 3 + 1 dimensional gravity with this canonical quantization, there are no fuzzballs. So that is true. There I use string theory. But when I started talking about a small corrections theorem, this has nothing to do with string theory. It works for bosons, fermions. I just took scalar field as an example. You could take anything. All we are saying here is that this is completely general. Just some unitary dynamics, but we don't know where it comes from. Could be any quantum gravity theory. All we assume is at infinity, I may not even have written graviton strings. It's infinity is normal. That's all we are saying. Infinity is like the lab. It's just normal place. With that, you just make any effective semi-classical physics like the lab. You can take bosons, you can take fermions, and then what is going to happen is your entanglement curve will not come down. So this is just like the Hawking's original setting, except people always worried that small corrections to what Hawking was doing could maybe fix the problem, because so many quanta are being emitted, there could be some delicate correlations between them that fix the problem. The small correction theorem is important because it tells you, no, the delicate corrections between large number of quanta do not fix the problem. It's not epsilon times n or something which is important for the curve. It's just epsilon. If epsilon times n had to be small, you could say, how can you prove anything? N is so big. The small corrections epsilon you may not even notice. It may fix the problem. But no, it's not epsilon times n that appears here. It's only epsilon. Okay. So then,
sorry, can I ask a short question?
Yes.
Yeah. So in the previous page about the strong subadditivity inequality, so I believe that the assumption includes the fact that the subsystems A, B, and C are independent. So may I ask, is there any possibility that in your exact quantum gravity picture, those subsystems may not be independent? So such that this, yeah, thank you.
Thanks for that question. Absolutely. And that's exactly what I was about to say now. If you want to beat the semi-classical theorem and this small corrections theorem, and you want the entanglement graph to come down, you have to violate one of the assumptions. And one of the assumptions was that physics out here is completely normal. And normal means that the degrees of freedom here are just like the local degrees of freedom in a normal piece of the lab. But if these bits here were somehow either connected, were somehow the same as the bits here, they were not independent. Like you can identify a bit here with a bit here, or if you have Hamiltonian interactions between here and here, it does not work. So that's what I'm going to call the wormhole paradigm. That's just a word because, in the initial paper of Suska and Maldacena, they drew wormholes like this. But anything in this category of things where infinity has is not just normal, local, what you think of as you could pick out from Green, Schwarzschild, or Polchinski, the physics of string theory in flat space, and not worry about the black hole far away, because this distance is very big. This is like, order m cube. If even there some connection to the inside remains, that these degrees of freedom are the same as these degrees of freedom, non-local identifications or non-local interactions, then you can beat the theorem. And that's what I'm calling the wormhole paradigm. I'm going to tell you my difficulties with the paradigm now, but that's exactly the point. If you want the graph to come down, as people do, they have to do one of these things. Exactly. So whenever they do one of these things, these non-local stuff, which right now we had removed from our assumptions, the moment you do anything from here to here, an interaction or an identification of degrees of freedom here and here, let's put all of those in what I'm calling the wormhole paradigm. And now I'm going to come and talk about my difficulties with the wormhole paradigm. So right now, just to summarize what I have said so far, the small correction theorem leaves you with two sharply different possibilities. The fuzzball paradigm, this guy is a piece of coal. That's what we are finding from all the constructions we've done over 23 years. You just get a piece of coal, it radiates from its surface, there's nothing to think about more. But then if you do want to make a semi-classical approximation, then you can have your semi-classical approximation, but at the price of giving up locality. So this is what I just call that the wormhole paradigm, for lack of a better word. And now I'm going to come and talk about my difficulties with that paradigm. To do that, let me first say, what is the wormhole paradigm saying in terms of nuts and bolts? Where does it actually interact with the kind of things I was saying with fuzzballs? So from what I understand, the origins of the wormhole idea, they really lie with the eternal black hole. So it's a long chain of work going back to Maldacena, Van Ramstonk, using old metrics of Israel. The idea was that if you take two CFTs, which are entangled, let's say in a thermofield double state, but not interacting, okay, they're not interacting, then what's the dual to that? And the idea was the dual to that would be the eternal black hole, which is connected, because this is one connected geometry. So even though these guys are not connected, there's no interaction between them, they're only entangled, here it will be connected. But I have put a question mark on that because I don't think this is correct. So really, we are going back to the first principles of the whole wormhole paradigm. I think right away here, there is a mistake. So what do I think the answer here is? So I think this is not true. Each of these CFT states here, the dual to that is just some fuzzball. So if I draw the dual of that as some, just in red, it's just like a piece of coal. So it's just ADS with something sitting in it, right? ADS with some structure in it. So I've drawn it like this. And this other guy is also its own stuff. You can always take two different things, like a piece of coal here, a piece of coal, in California, in state I and state I, and you can entangle them. But they're just two entangled pieces of coal, and that's all that you have. So the dual to two of these, according to me, will just be this. And I showed that if you actually argue that it is this, you run into some troubles. Okay, so let me not talk about the troubles, but I'm just trying to say what the basic difference is, because my goal here was to contrast the fuzzball paradigm with the wormhole paradigm. And this is where the difference starts. The dual to two entangled CFTs, according to me, is just that each CFT gives you some states in the bulk. States just end over there. And then, they're just entangled. So Here's the exact model. For the two-charge extremal, we know all the dual gravity states. For each state in the CFT, this is a two-charge state. It only has D1 and D5 branes. It doesn't have the P thing of Strominger and Waffa, but it's still a good model for the black hole. It's dual to the model that Ashok Sen actually worked with. And this is called a two-charge black hole. It behaves like a black hole because entropy also goes like product of the charges. With 3 charges goes like this, with 4 charges square root of 4 numbers. They're all in the same type. So I call them all just the same category of black holes. But the good thing about this two-charge black hole, that even though it's very small, it's sort of borderline of being a black hole, you can solve everything exactly. So for all the states contributing to this entropy, you can count them in the CFT, but for all of them, you can also make the gravity dual. And we know them all perfectly in every way. It's been worked out to death. And all of them are just like these caps. You just come and you find some structure here. It's just some metric, some structure there, various string states here, and they're just like pieces of code. So now let me take one of these things here with size, let's say 1 meter. I make something D1, D5 bound state of 1,000 branes, make some kind of a dip in space-time of size a meter. And a long distance away, 1,000,000 kilometers away, I take another such thing. And its dual is here. I can entangle these states. I can have some branes in my room, some branes in California. I can take an entangled state. But on the gravity side, I just see a little pit here with some structure. I see a pit here with some structure. To me, they don't look different from pieces of coal at all. We know exactly what these guys are. So to me, they just look like two well-separated but entangled pieces of coal. And I think the story ends here. There is nothing else. But the wormhole game seems to be saying, no, if I entangle two things like this, there is something more. There is some kind of a identification of degrees of freedom or interaction, or we'll have to come to see what that is. We'll talk about what that needs to be. So, but what are these effects? What is this stuff extra? Because we've already made these duals and we don't see anything. Of course, this is a very simple case. And you may say, if you look at more complicated cases, you will see this. But the whole issue is the following. You take two things which are well separated, but entangled. Is there anything more than two well separated but entangled pieces of code? So let me now just go to, so that's the issue. So I'm disagreeing with the wormhole picture right from the beginning starting points about what is the dual of two entangled CFTs. It is not the eternal whole in terms of what I'm saying. And so now I'll talk a little bit about my computations, which motivate the wormhole picture. This is work in the last couple of years, but it's the work of other people, not my work. And so let me apologize in advance for any errors that I'm making in representing what they are saying. And if they point out these errors while they are here in the audience, I'd be very happy to listen to any mistakes. So these comments I'm making here in this part of the talk, they should be taken as a starting point for maybe more detailed interactions with people who want to talk about this. But this is my understanding of what I have read over the last 2 years from all these papers. So let's first ask, can simple 2D gravity computations, JT gravity or something, can it show that the page curve actually comes down? People say the page curve comes down from a simple JT gravity construction. So the whole problem was that the entanglement was rising in the Hawking picture. If you add small corrections, it still keeps rising. That's the small correction theorem. How do you actually use simple 2D gravity to show that the page curve comes down? And so I think, no, the 2D gravity constructions cannot show that the page curve comes down. So there are many different computations that seem to suggest that it does, just based on using 2D gravity. I mean, I do agree the page curve comes down, but that's only from the fuzzballs, right? Because you don't have a smooth horizon. But the belief in these papers that do the page curve is that we won't have a fuzzball. We do have a horizon to some approximation, at least in the semi-classical approximation, we see a horizon, and still JT gravity will somehow miraculously tell us that the page curve comes down. And I'm saying, no, that can't happen. So let's dig into that a little bit. Okay. So each of the different computations I'm going to talk about, they have a different kind of issue with them. So let's look at a few different examples to illustrate the kind of things I'm worried about. So first, let's start with Euclidean computations. Some of the initial computations were the Euclidean geometry. But there's a very basic issue with these, which let me just state. It's a very abstract issue. Where are the states in any Euclidean calculation that actually cause the information paradox? This has nothing to do with what is being done with JT gravity now. This is an old problem. So what was the old problem? So if you take the Lorentzian hole and you analytically continue t to minus I tau, you get the Euclidean geometry. We all know that, and has this periodic identification. It looks like this cigar, this periodic identification beta. The geometry only ends at the horizon. It's only in the range to infinity. So the interior of the horizon is not even here, the Euclidean geometry. You can certainly add handles to it. People these days talk about, we have missed out handles, we should do that. But Gibbons and Hawking, who got this kind of geometry, they would certainly agree that if you want to add handles in the full quantum gravity theory, they will probably be small, the corrections, but by all means do so. So when I write Gibbons Hawking and say, I'll compute the action for this, you want to add handles, please do so. And then what do Gibbons and Hawking do in this 76 paper? They compute the action for this. And if you want to add these, you can. Then they compute from that by the usual thermodynamic relations and entropy, and you find the answer A/4G. Okay. But we have seen that the information paradox is created in the Lorentzian section by these slices on which you can explicitly see that you can put infinitely many states. So how are we getting this finite entropy, and what is the meaning of this finite entropy? So if you just do this action for this and convert the action to an entropy by the usual thermodynamic connection between free energy and entropy, action is free energy and then log of action is free energy, then the entropy is from there, then you get a finite number. But then if you actually write down the states, you get an infinite number from Hawking way or bags of gold, all the different ways we saw of writing the information paradox. So the information paradox can be restated as the mismatch between the Euclidean answer and the infinite number of states that can be explicitly constructed in the Lorentzian answer. Okay, because right from 1976, we have known that if we were allowed to say, let's assume the Euclidean answer gives the correct count of states, then there was no puzzle from the beginning, because as the whole becomes smaller, the A/4G goes to 0. And if there are no states there, you can't entangle with them. So then you will say the page curve comes down. So why didn't we say in 1976 that we have the Euclidean answer, so that's the entropy. So when the black hole goes away, there's no entropy, you can't entangle, the page curve comes down. And the reason was the following. Because the Euclidean computation, if you slice this and you see what states you are seeing here, which are running in that loop, the states which actually gave rise to the puzzle, the ones with all the inside the black hole having all those positive and negative energy modes, which give you the more than e to the s back states and all that, they're not here. So the whole problem was that the states which actually gave rise to the puzzle were not in the Euclidean section. So normally when you take a Euclidean one loop path integral, you see the path integral going in some kind of a thermal circle, periodic Euclidean time beta. But when you cut it in the horizontal section, you see all the states of the theory running in that loop, weighted with e to the minus beta times their energy. But in the Euclidean section, those states are not there. So that's just a restatement of the paradox. This was the paradox, that the things which give infinity don't actually have the states. And in the Euclidean calculation used to argue for the recent wormhole or the island kind of scenarios, I have the same worry. I go back and I look at them and I try to see if I slice their Euclidean path integral construction, the amplitudes that they draw, the states which were actually leading to the paradox are actually not there. The mismatch between Euclidean and Lorentzian actually was the paradox, right? So this is the problem I have with the Euclidean answers. I'm not going to focus on Euclidean anymore because of course, a lot of papers have been talking about Lorentzian. And note before we go to Lorentzian that the page curve is actually only defined for Lorentzian time. You have to emit something, right? As a function of emission steps or as a function of time t, you want the page curve to come down. The Euclidean theory doesn't even have any page curve because there's nothing here to entangle with anything which is large anyway. If you just take a cigar geometry, you'll get an entanglement of some part of the part outside the black hole, some other part outside the black hole that has nothing to do with the entanglement which is actually causing the puzzle. So let's go and look at what the Lorentzian papers say. The Euclidean ones could be taken as motivation, but really we should go to the Lorentzian papers. And now so then we have these states, and we could actually evolve in the Lorentzian section, starting with maybe the infalling shell, do some evolution to end up with this state on some slice. And then what do people do with that? You prepare many copies of that state. Then you join these slices across some edge so that you actually make like trace row square. You try to make Rényi entropies. That's the kind of game that people do. And if you do that and you compute the entanglement entropies or Rényi entropies by taking, let's say, 2 copies of the state, gluing it on the inside to make a density matrix for the outside, the way you must have heard in many talks, you do that, you find the entanglement curve is actually rising. It's not coming down. Okay, so then what do people do? How do they get a page curve coming down? They add a prescription where the dot product inside is going to be modified. Okay, so let's look at what the modification is. And then they argue that with the modified dot product, the entanglement graph will come down. But we'll now actually argue that this modified inner products that they are going to use are equal to putting non-unitarity of evolution in the black hole interior. Now, if you have non-unitarity inside the black hole interior, there was no difficulty in solving the puzzle. That is Hawking's original answer. If there were 100 states in the black hole, but they evolved to 99, 98, and then down to 1 at the end, that 1 is the vacuum, the black hole goes away, there is no problem. That was the original thing. So let's go and see where is the non-unitarity. So let's take an example. Let's say look at some of these papers, but there are many papers which are very similar. But I like this paper because they said very clearly that infinity is separate. It's what it is. There are no interactions, wormholes from here to here. Okay, so I said that's good. Let's focus on that. At least if you have locality, then something must be going wrong. What happens with the small correction theorem? Let's drill in there and see. So they try to compute Rényi entropies, and for that you need to compute trace of rho of the radiation, density matrix on the radiation squared. I'll assume that people have seen these kinds of calculations before. If you haven't, then these slides may not make that much sense, but then we can come back to the other arguments. You don't have to know these slides to understand the rest of the talk. So then just bear with me for a little bit. So the way they compute any entropy is that they make 2 copies of the state. You trace it appropriately on the interior to get a density matrix between this state and this state. You can make another copy of the density matrix between this state and this state. If you join this to this by tracing, it becomes matrix multiplication, like rho square. And if you trace this with this, it becomes trace of rho square. So just by taking traces of various things on several copies of a state, you can make anything like trace rho square, and so on. So I'm just trying to depict that story. This is the outside. This is the gravity region. So that I've drawn it all with these curves. But then we have to allow something new. What do I mean by something new? The 2D gravity, which all these papers are working with, was solved. The 2D quantum gravity plus scalar field was exactly solved by CGHS in 93. And we know that information doesn't come out there. They got the page curve just going up. So something new has to be done. And if you ask what new could you do in 1+1 gravity, well, the one thing that CGHS did not put in was the fact that your line segment can go to other topologies. What do other topologies mean when you do a Lorentzian evolution? The only thing you can do with a one-dimensional segment is to break it. So the segment can break into many pieces. Okay, so that will allow. That's the new thing. We want to add topology change. So that's the only thing you can do. But this thing, physics is confined here, no non-local effects. Infinity is a normal place, so I'm writing that up. Again, if we compute trace rho square using the normal inner products in here, you find the page curve doesn't come down, it keeps going up. Okay, so then they're going to change the inner product and they're going to argue it comes down, and we want to drill in there and see what to do. But before we do that, let's ask if in any of these calculations, how are they using the fact that what they have here is a black hole with a horizon and not just a piece of coal? Because if it was a piece of coal, the curve has to come down. So in any calculation you see where people show the page curve is coming down, first you have to go and ask, where are they putting in the fact it's a semi-classical horizon with pair creation? If you don't see that in the paper, then talking about a piece of coal, and of course the page curve can be made to come down. So that's very important. So I just drew this slide here. Suppose these were pieces of coal, and then you can do the same stuff, compute trace rho square. And then in fact, there's this beautiful paper of Liu and Worthen from last year. If you look at section 2 of that paper, they show how for a normal system, the page curve comes down and you look like you're having all the different saddle points and you can run the whole story. And here there is no mystery, just an ordinary system like a piece of coal. But because it's an ordinary system like a piece of coal, the input into the calculation done by these people is that the entire Hilbert space is bounded. You have a finite number of bits there. You can't actually create new pairs. The whole point was the new pairs brought in new bits inside. That's why the entropy inside kept increasing. But if you fix the number of bits inside, so if something has to go out, one of the older bits has to leave, then you get the normal system, and then there is no puzzle. So we have to put in the fact of the smooth horizon, otherwise we're not even doing anything. So now I have put it in. So again, I'm following all these papers saying, the Marov-Maxfield kind of papers saying infinity is a normal place, and I have put in the smooth horizon, so pair creation is going on here. But here I can do what I want. I can break these slices, I can do whatever, but then you find the entanglement curve is going up. How do they get it to not go up? Well, they say we are going to change the inner product. So how do you change the inner product? Suppose you have 2 copies, they're going to compute trace rho square. So 2 copies, this is copy 1, bracket, copy 2, bracket. So normally the dot product between copy 1 bracket and copy 2 bracket would have been this one. Each bra dots with its own ket, they're 2 completely different copies. But they say, no, we'll modify it so that it's symmetrical. You don't dot this with this and this with this. You do this dot, but you can also dot this way. Once inside, all these broken pieces can switch. You can join it any way you like inside, and all these models giving the different topologies or the different saddle points or the replicome, they're all basically doing something like this. So let's just take this as a toy model for now. This just which comes from the trace rho square, and ask what does it mean. If I look at this dot product now, I'm acting it on these 4 states. Let's call it 2 states of this as 0, 1, states also of this as 0, 1. So there are 4 states of any 2 guys. So we have 2 states, this has 2 states. Then there are 4 states. Take a toy model for that. So the 4 states are 0, 0 for each of them. Let I and j be 1 and 2. Then 0, 0, 1, 1, 0, 1, and 1, 0. The dot product, if you write the dot product over here, this dot product gives you this matrix. If you look at this matrix, you find this has determinant 0. You can see this part has determinant 0. And in fact, this state has vanishing norm. So whenever you say, no, I will do some path integral, which effectively gives me a new dot product, be careful. Not every path integral is harmless. If you actually go and see what prescription you have given, the dot product you have for that, if it actually is going to kill some states, kill their norm, you basically have non-unitarity, which is exactly what Hawking said in 75. If you take multiple states and crush them down to one state, the vacuum in this particular case, or something like Horowitz-Malthus, final state boundary condition. You have many states inside, but they all have to go to the vacuum before the black hole ends. Anything like that is a prescription for non-unitarity. And here, you can directly see it working over here. And I think this is a basic problem for trying to do any of this picture, which I see sometimes in Juan's talks or other talks. So this kind of picture, I think, is the one that Juan would draw for what happens at the end of a black hole evaporation. So you have this kind of good slice here. The inside part is the island, it's the radiation over here. But when the black hole evaporates, the island splits off into a baby universe. So some papers say this. Let's stay with that for the moment. But then you could have another copy of this. So you're trying to compute trace rho square by dotting this with this and somehow joining the islands. But you treat these baby universes as interchangeable. Like this one can come here or this one can go here. This is what people are doing to make all these replica wormholes kinds of things. Replica wormhole is Euclidean, but there are many, the Lorentzian versions of this seem to be doing this. But there is a problem with this. The moment you do this, the problem is the following. We have to be careful. Suppose you have multiple copies, let's say 3 copies, in general n copies, and each one has these entangled pairs. So up to here, if I create entangled pairs like this, the entanglement of the outside with the inside is n log 2. That's what we said there, n log 2. I've taken n copies of something, the n log 2, because there are 2 to the n states in here. If these can each be 0 or 1, if there are n of them, there are 2 to the n states. But suppose I say the inside breaks off into a baby universe. Yeah, broke it off into a baby universe, and the baby universe state is just given by what quanta is sitting on it. So if they're identical baby universes. I can join this one here with this one here. All those different ways of joining are allowed. But if they're identical and I put on them this kind of a dot product, the number of states you have in here, if there are only 2 flavors for each of these, let's say that I took in this model, they're only n plus 1 states. Okay. So the 2 to the n states has been crushed to n plus 1 states. And so the evolution which they are assuming automatically is not unitary. So let me just talk about one more thing, and then I'll sort of end and sort of go to my conclusions. I'm almost out of time. So the recent attempts to come all this page curve stuff, if you go back to where all this was starting from, how did we get onto all this non-unitarity and all this? A lot of them started from the Ryu-Takanagi relation, which by itself is very beautiful. That you have ADS in the vacuum, let's say vacuum ADS, and then you want the entanglement of this part of the CFT boundary, region Q with the remainder. If you take the area of the minimal surface, then A upon 4G gives the entanglement of this with this. Okay, so you can check it and it works out. So, but let us ask, what can the RT relation tell us? What are we drawing from there, which is taking us into all these strange directions about black hole physics? So can we extract any evidence for the idea that there cannot be more than this many states in a region with area A? That's what somehow all these arguments are trying to argue, that if you have a few states in some region with boundary area A, only a few states, the entanglement with that is given by the number of states. But if you put too many states here, the entanglement saturates, it can never become more than A by 4G. If you look at the output of all this, replica trick or new saddle point or any of these ways of doing it, they're all trying to argue if you put too many states in some region, you can't put more than this many states, or at least you can't entangle by more than that. That's what they are going for. But this is an old idea from Bekenstein. Bekenstein was basically saying in a region of area A, you can't put more than S Beck degrees of freedom. But that was the whole information puzzle. When you actually go and make the states in the black hole, you can put more than S Beck. So that contrast between what Bekenstein was proposing and what we actually find is the puzzle. So let's see what the RT idea can tell us. So we're actually trying to prove this, that if we put too many states here, after some time when we reach A by 4G states, we can't put any more. But actually the RT is not going there at all, because here we don't have any states. We have no excitations. It's not like we're making many states and finding we can't put more than this many guys to entangle with. The entanglement actually is in the CFT. The area is in the bulk. This is the vacuum, ADS. This is also in the vacuum of the CFT. So we are in the vacuum state. What entanglement are we talking about, which can possibly tell us that in a region of area A, you cannot have more than so many states? So if we just look at it carefully, this which we are looking for is not this at all, because here the area is in one theory, the bulk, the entanglement is in a different theory, the boundary. So actually, I think there's some conceptual things here. We have jumped too quickly from some rough things to do with area we saw in the RT prescription to where we are using it for black holes. Okay? So I think you can certainly put a black hole inside ADS, but I think the correct interpretation for this expression is that you just put a fuzzball there, and that has E to the S states. And the picture that is coming out of the wormhole scenario, however, is very different. If you make a black hole, you can actually entangle with it very much. by more than S spec. But the degrees of freedom in the island here are entangled with the radiation, the entanglement wedge of the radiation, as they call it. And the CFT only describes degrees of freedom up to the QES surface. And these guys are in the island, and they really are not described as the CFT, but they go here. But I think the RT doesn't tell us any of this. The arguments going from the RT up to here, if we go through them, I think they don't work. And I think the answer is that the A by 4G is true, but each of the states you're counting in A by 4G, the complicated CFT states correspond to black holes, the dual is just the fuzzball. There's nothing wrong with ADS CFT, but this is the answer. Okay, so let me try to end because I'm basically out of time. So I just have some slides to summarize my ideas. Can I just take another 5 minutes? Will that be okay?
Yes, yes, please continue.
So what does all this mean? Okay. So I think with all that we have seen in string theory, there's no alternative to the fuzzball paradigm. And the basic lesson we are learning is that the scale of quantum gravity, normally you would think it's Planck scale. And it's true. If you collide two gravitons, till the wavelength gets below the Planck scale, quantum gravity effects don't start. That's true. But if you collect a large number of quanta together, some big number n, the lesson we are learning from string theory is that the scale of quantum gravity is not Planck length, but some power of n times the Planck length. And that is always allowed on dimensional grounds. On dimensional grounds, we always thought quantum gravity has to be at the scale LP because that's the only thing you can make out of G, H bar, and C. But once you have a big number n, you're trying to make a macroscopic object, it could have been this, or it could have been this. And what we are learning is, in string theory, it is this. Okay? And anybody who's trying to ask for the semi-classical approximation is then forced into these kinds of non-locality, the non-local identification of bits, or something funny, which I have disagreed with. I have said that's not there. I think what's wrong is in trying to ask for this. If you don't want to ask for this, the story is already over. So why are people having these disputes? I think there are two reasons that people have gone in this direction of the wormhole paradigm, which I think is not correct. And I'll just try to state those two lessons and then stop. So I don't know any evidence from string theory that we really have non-local interactions across these big distances. Okay, we know strings, brains, strings between brains. Nothing actually gives us this. So why are we thinking about this? And I think the reason that people are thinking about this is that they are trying to extend an analogy from ADS CFT, which I think is not correct. So just write down what ADS CFT does. You take a stack of D3 brains sitting in flat space, you throw a graviton onto it. Then the graviton breaks up into lots of open strings, right? Which are described by gluons of Yang-Mills, and then get some mesogravitons. And if you wait for some time, it becomes a bigger blob of gluons. And so there's some dynamics here. But if you represent these D3 brains by not just the D3 brains, but just by an empty ADS, and you send the same graviton in, you find you can map the same dynamics 1 to 1 onto by saying it's just gone deeper into ADS. You go make the bigger blob here, it's deeper into ADS. So the spreading of this blob in the open string description can be mapped to the deeper progression of the graviton in the closed string description. And so we have this map. And I think this is beautiful. But what this suggested was a very complicated description here might be given by a very simple description in some other language. It's very beautiful. And here it's true. But then you start thinking, could the following thing work for a black hole? You have something very messy here. And if you want to do like the analog of the open string description, it is messy, but perhaps there is some simplified description where it actually looks like simple gravity, where local gravitons are moving, behaving like semi-classical gravity, at least for short times. And so why can't we have this approximation? ADS CFT would suggest we should have something like this. But actually, this is not true. I think this is what suggested the idea of having that we should take the semi-classical approximation seriously. But we have seen the exact theory doesn't actually allow that. Then we need non-local effects. So why are people thinking like this? The analogy actually is the problem. It's actually not analogous. If you look at D3 brains, the bound state of D3 brains has only one state. It's a unique ground state. Doesn't matter how many D3 brains you have. It's just one state. It's one supermultiplet of size 256. It doesn't grow with n. So the entropy is just fixed. Let's call it S equal to 0. And the ADS space is just a unique space. It has no structure and one state. Entropy is 0. This can be mapped to this. But a black hole has entropy. In fact, the size of the horizon is given by how much entropy it contains. Once you have the size of a surface given by the entropy it contains, you can't apply the ADS CFT kind of idea about getting an effective description of that state by something which is analogous to the ADS CFT map. And the reason is very simple. There's so many different states here. You can't map them all to have the same effective behavior. They all have to behave differently. If you make any map where they start behaving the same as each other, you will lose the information. We can actually see this quite explicitly for this two-charge extremal D1, D5 system, which we can solve exactly. In the nice geometry of D1, D5, which is analogous to semi-classical geometry, just have one metric. But you know there can't be one metric. There's an entropy. We can count it from the brains. But now we have also made it in gravity. We make all these fuzzballs. And you find once you go deep down and up into the throat, you get these different caps. And each different shape of the cap gives you one state, and all the states account for the entropy. So what you find is just at the place where the horizon starts coming up, at that place, all the geometries actually start differing. So you can see here explicitly a case where if you have many states in a region, in the region where the A by 4G counts the states, inside that the states have to differ. You don't actually get the semi-classical approximation, and the idea of replacing them by one geometry doesn't work. So I think that was one mistake. And the other mistake that people seem to be making is that Hamiltonian interactions we know generate entanglement. Right? If you have two coupled harmonic oscillators, this is the coupling, then the ground state of the total system will not be the ground state of one times the ground state of the other. It actually looks more like this. It has all this thing. So it's entangled between the two oscillators. We know that if two things are interacting, they will generate entanglement. Same thing happens in ADS-CFT. The CFT has entanglements across the circle because different points on the boundary are talking to different points on the boundary by the Hamiltonian. But the reverse is not true in quantum mechanics. Entanglements do not imply an interaction. If I take one electron here, one electron on Mars, and I entangle them, it does not mean that there is an interaction between them. But somehow using these ideas of entanglement wedge reconstruction, people seem to be believing that if I entangle two things far away, there is some kind of effect between them. And I think there are no effects of this kind. Entanglement doesn't do anything that people seem to be thinking. People seem to think is very important, but actually entanglements can't do anything. If let's say you have two quanta in the state 0, 0, and suppose that state evolves to something psi 1, and you take 1, 1, it evolves to psi 2. Both are factored states, no entanglement. Then now if you entangle them, you actually have no choice. By the linearity of entanglement, you already know it has to go to psi 1 plus psi 2. So entanglement never does anything new. If non-entangled states can't give you any interesting physics, then entangling them cannot give you anything by the linearity of quantum mechanics. So I think this basic idea that entanglement can generate space-time, I think that's wrong. So there's a lot of talk about this, that entanglement generates space-time, but I think that's not true. And I think that's what the kind of thing which is leading to a mistake. So this was my final slide. There are all the different constructions of fuzzballs, and I think this is the only paradigm that works. I already talked about this slide. And with the wormhole paradigm, you either must have non-unitarity here, or you must have these non-local effects. And I just drew them here. But once you look at everything carefully and with the small correction theorem in mind, you find the wormhole paradigm, which is the opposite to the fuzzball paradigm. That is, you want to keep a smooth horizon. Your only choices are non-unitarity or non-local interactions. So let me stop here. And anybody has interesting comments for me on more about the wormhole paradigm, about things I have not understood, please tell me.
Okay, thank you very much for your interesting talk, Samir. Question, please. There are some people, let me see who. Robert, please ask your question.
Yes, I'd like to ask a question about the remnant paradigm.
Yes.
So, for example, if you have a new universe inside of a black hole,
Yes.
do you see, what are the problems which you see with that?
Okay, so in principle, you could have the remnant paradigm in some generic theory, right? I mean, the difference, let me just mention the standard difficulty that people have, and then let me say what are the extra things from string theory which makes me not want to go in that direction. So the standard things, of course, are if you want to make, let's say, a baby universe, that's one of the standard things to do with the remnants, right? That you want to open up a little neck inside the Planck remnant and do that, then as you know very well, at the neck, you need to have some violation of the positive energy conditions, because otherwise the Raychaudhuri equation tells you once you narrow a neck, you can't open up. That's not a serious problem, because you could always say that locally with quantum fluctuations, you could make a effectively negative energy density by Casimir kind of effects. So maybe you can make that neck. So if you want to do that, you can, and then you can open a baby universe inside, and then you can just go with that. And so if somebody has that as a solution, I think with a generic gravity theory, it's fine. Okay. The difficulty I have is that when I come to string theory, it seems there are too many things telling me that in string theory, something else happens. And that goes all the way back to what we see from, let's say, Strominger-Waff, right? With the remnant kind of picture, the A over 4G does not actually give me the count of states in there. It just tells me how many states I can exchange in a given time. But instead, I can store as many with the baby universe inside or the remnant inside. But in string theory, somehow the count of states has suggested to us that we can't do that. Okay. Of course, you can say Strominger-Vafa was extremal, and you would like to go non-extremal to talk about baby universes. But the near extremal physics has also worked out quite well, at least in terms of numbers. We don't understand all the dynamics that well, but in terms of numbers. So I'm just saying that in string theory, somehow the idea that we could actually disconnect a piece of something, we have not been able to construct it. If there was a baby universe, because we actually make things at the scale of strings, brains, we do Planck scale physics, we should have been able to make something where we can concretely show that at least a tiny baby universe which separates out from the rest of space-time but contains, let's say, 3 Planck units of energy, we should have been able to make that as a construction out of 3D brains. But because we don't do that, because we haven't been able to do that, I tend to not believe in it. But that doesn't mean one can rule out remnants. You can have remnants in a theory, maybe not in string theory, but in some other theory. Does it answer at all what you were asking?
Yeah, but let me follow up. Sometimes I hear arguments about divergences in scattering matrix elements if you have remnants.
Yes.
What is your view on that?
So those arguments are there, but they're also not very difficult to bypass, right? The argument is there are infinitely many guys of Planck mass, that if you make a loop diagram, then all these guys will run in the loop. And so whatever the contribution of one guy might be, once you multiply it by infinitely many possibilities, the amplitude will have to diverge. But for that, there were some arguments long ago by many people, I think Strominger was one of them also, that as you make more and more complicated remnants, that is the ones which come from starting from bigger and bigger black holes and then becoming remnants, suppose that couplings were smaller and smaller, they were more difficult to couple to things outside, then you could arrange it so that the couplings of the more complicated remnants are smaller and smaller, and the loop amplitude will actually converge. So if one actually makes a baby universe which is very deep and doesn't couple very strongly to anything outside, and more complicated universes have a smaller coupling to the outside, you can bypass that. But I think we know so little about remnants that I think that one can't argue either way about that.
Yeah, thanks a lot. It's very clear.
Okay, next question from Mikhaila.
Yes, thanks for the nice talk. So I have a very naive question. The first issue that you discussed on ADS CFT. So whether the thermal double of CFTs is really dual to a double-sided black hole or not. So yes. I would naively say that the quality of the correlation function supports the duality. Basically, when you apply the usual prescription, you indeed get the correct CFT correlator from the black hole. So what's your comment on that?
Yeah, so let's talk a bit about that. And so you could take a look at this paper where I actually showed what is actually wrong with this. So certainly if you take correlation functions here, you will get some answers simply because they're entangled. So something here will correlate because they're entangled, simply because of the correlations. But you will get the same answer from here also, because if you have two things which are entangled and you measure, this is just a description of this, right? For me, this is just open string language, rewritten in closed string language is just a rewriting, it's just variable change. So same answer will come from here also. But if this same answer could come from here, you would say, okay, that's at least interesting. But there's a problem. So what's the problem? The problem is the following. Suppose I throw some energy into this, let's say a spin up here, and I let it radiate out some energy back from here so that that information comes back out to me. Now, if I throw a bit here, let's say it's having spin up or down, the information can only come out on this side. I can't pick out that information by looking at this CFT because they're not interacting. So everybody would agree with that. How do I see that in this diagram? Well, at first you might be very happy that if I throw something from here, you see it doesn't go to the left universe because it falls into the singularity. So the guy seems to be very clever. It's not actually allowing interaction from one side to the other. Unfortunately, that's true only at leading order. And what I did in this paper was I said, what happens when you look at the actual semi-classical effect that lead to Hawking radiation, the one loop corrections, and then you find there's actually a contradiction. And the contradiction is the following. Let's send one particle from here, one particle from here, if you like. Or let's just send one particle from this side. Once it goes in here, there'll be Hawking radiation. And the Hawking radiation will happen at both horizons. And so some part of the information comes out here, some comes out here. Let's assume the information does come out of the hole, right? We don't know how, but let's say it comes out. So if it goes in here, it comes out this. Once the guy has gone in here, there's no way to prevent the information from coming out at both the horizons mixed up. You can make it even more interesting. You can send one particle from here, one particle from here. In this picture, this information can only come out here, here it can only come out here. But here these two collide, and suppose the two particles collide and create three particles. Let's take a 2 to 3 interaction. Now those three particles are completely mixed up in their information between the left and the right. How do you make sure that the Hawking radiation at these two horizons carries out this piece of the information here and this piece here? How do you separate milk and water having once mixed them? So once you look at what the Hawking radiation is doing in this setting, and assuming the Hawking radiation is unitary, you run into paradoxes. And so that's what I discussed in this paper, that at leading classical order, it looks like everything is okay. And the things that people checked, they were going to work out regardless, because the 2-point correlates they worked out here, many correlates that you do, they come from the Euclidean cross sections. If you take the Euclidean diagram, they're just thermal correlators. Okay. If you analytically continue that on both sides, you get Lorentzian theory here and the Lorentzian diagram here. If you get a Euclidean answer, you analytically continue both the gravity and the CFT, it'll appear to match. But it's only because you compute something which doesn't actually have a Lorentzian description. Something which can be mapped back to Euclidean is only an analytic continuation. It's actually not really Lorentzian. Real Lorentzian is something which actually has like Hawking pair creation. It's not then the Euclidean answer. Anything periodic cannot actually create pairs. Right? So the point is that you have to actually go to a really on-shell Lorentzian process, which is not coming from a Euclidean process. And then you find that there are contradictions. This thing gives you things which this thing should not. And that's how I argued to myself that this doesn't work. If you want to save it, you will need wormholes connecting here to here. I talk about that in this paper, like what kind of wormhole interaction will do this, but it looked a little far-fetched to me. I mean, you don't really have wormholes from here to here, in my opinion, but without those non-local wormholes, you can actually show sharp contradictions. Does that answer what you were asking?
Yes, yeah, thanks. Thanks.
The next question from Luca, please.
Yes, thanks. Thanks very much for the talk, Samir. I would have two questions. So the first question is related to this contradiction that you mentioned between the Lorentzian and the Euclidean computation of the entropy of the black hole. So it's still not clear to me why there is really a contradiction, because let's suppose we start from the Euclidean computation. If you do the Euclidean computation, just evaluating basically, this formula you are showing, what we are really taking into account are just gravitational degrees of freedom.
Yes.
Okay. And we are getting this area law. Now in the Lorentzian picture, for instance, if we imagine the ingoing flux of the Hawking radiation, okay, so in this case we would have let's say the gravitational degrees of freedom plus this ingoing flux of matter, which in principle would increase the entropy, and this would give rise to the paradox, as you said. Okay, but it's like that. I mean, why the two computations should really give it the same? Because in the Lorentzian picture, it seems that we have some ingoing flux which has negative energy, which will decrease the mass. Okay, but this does not mean that the number of states should also decrease, because the number of states could very well be larger because we have negative and positive contribution in energy. And in principle, in Lorentzian picture, just because we have this extra ingoing flux, we would expect something which is bigger than the area law. And so we would say that basically, indeed, the black hole system, including also this ingoing flux, would have an entropy which in total is larger than the area.
Okay.
So why this?
I think I understand the question. Yeah, okay. I think I understand the question. So the point is, when you look at this and you ask what this is computing, actually, let's put them both in exactly the same setting. So what do I mean by the same setting? Here, let me assume that all these particles are just gravitons. I just take gravity. So the gravitons, of course, they're in gravity. So I have to include those, right? I will not put any other matter right now. So let's just take gravitons, which are already in gravity. And that's the ones whose thing I'm counting here. Then here also, when you look at this, this is the black hole geometry at a temperature beta. So if you actually draw this whole thing properly, you find that in this region outside the hole, like 4M, 6M, 8M, it's actually full of gravitational radiation, the same gravitons at the temperature of the black hole. Because you're still having a thermal loop, right? If you have a thermal loop, now go away from the black hole, because the thermal loop here, it has to be full of the same gravitons. So this black hole is actually in equilibrium with the heat bath. That's the only way that this thing actually makes sense, because you put it at temperature beta. So in principle, I'm actually counting the same things. I have taken only gravity, put it in a thermal circle at temperature beta. So it has all the metrics, plus there are small fluctuations. And the small fluctuation, including gravitons at temperature beta, which it does, those are all supposed to be counted by the path integral. So the leading order saddle point may count something, but of course, I'm supposed to do the one loop fluctuations around it. If you do the one loop fluctuations, it actually counts the entropy of these other gravitons. And so people do that also. They add it in here. So you can do all that. But so let's assume that all that is done. You're adding all any handles or any topology change, also any one loop determinants. Once you put all that, the entire path integral is done. So in principle, you're counting everything in gravity, including gravitons. And then you come here and see what do you have here. You have drawn a space-like slice. On the space-like slice, you have only gravity and all the possible states of the graviton, such that at infinity, the mass is m. And now you find the number of states whose mass at infinity is m is unbounded. And now you say, I don't know what to make of it, because I took the same theory each time, same excitations each time, but the actual states only live in the Lorentzian section. Euclidean is not a theory, right? I mean, theory really lives in the Lorentzian section. Euclidean is only a trick. You're supposed to take all the states at any given time, then write an imaginary time minus beta, e to the minus tau, and then evolve them in a loop. That's just a way of counting them. But if you ever slice it like this, you're supposed to see all these states in there. If for a normal system, you will. Doesn't matter what normal system you take. If you slice it horizontally, it's going to be a cylinder, and all the states that contribute in the Lorentzian section will be running in that loop, each weighted by e to the minus beta times its own energy. And this time you say, those states are missing. So whatever this thing is giving me, I don't understand what it is. But your question is very relevant. If this was counting something, and here I was putting other degrees of freedom, they would not match. But the point is, I'm not doing that. Just gravity plus gravitons here, gravity plus gravitons here.
But instead,
Okay.
in the case of the remnant, you would count these extra degrees of freedom in the Lorentzian picture, and you would
Yes.
say that we have a larger entropy, right?
Absolutely. The remnant is honestly counting these guys. So remnant is not saying that these guys vanish or there's something non-unitary. The remnant just says that they stay there. If the evaporation ends at the Planck scale, then all this which is inside, this thing comes within Planck distance of the singularity solve, very close by, but all these guys stay there. Or you can disconnect the remnant and say it's a baby universe. You can break it. Okay, but then that's your remnant. It can disconnect or it cannot disconnect, but it all stays there. That's an honest solution to the problem because everything is still there. What I'm saying is that what is happening these days when people are saying somehow we managed to bring the page curve down, you can't bring the page curve down. If you go and look to see where these guys went, it's either non-unitarity, which is hidden, so it's not so clear, or it's non-locality, where something actually moved out, like by a wormhole, it was sent back out to infinity. And somebody can say that. He can say that in string theory or some theory of gravity, these quanta inside can travel through a wormhole and end up near infinity where the radiation is, and that's a solution to the puzzle. Yes, that's fine. But that is what all these calculations are actually telling you. If they're saying that they managed to keep a smooth horizon and get a page curve coming down, either this guy ends up here or all this stays in a remnant. There is no way you got the page curve down and everything else is normal. And there's a smooth horizon. You can't do that. That's a small correction theorem. You can't do everything.
Okay, I also have a question. Maybe I can give space to the other people. Then the other two people. So.
Okay. Next questions from Sravan.
Hi. In one of your slides where you said the scale of quantum gravity will be shifted by n power alpha times LP. That means if you have very, very large number of states, you basically go to kind of IR regime, right? Well, my question is related to actually not the non-locality. You're speaking about non-locality in string field theory. If you take any scalar field with some non-locality, there is a microcausality violation. If you say that the Planck scale is shifted to very all the way up to the IR, that means there is a macrocausality violation. Am I correct? And then
so no, I would not say that. So let me just say a little bit about that. It's very important. So let's take string theory. So suppose in string theory, you have extended objects, right? So you can have a big string loop. And let me take another big string. So it looks like if the string is 1 meter in diameter, there's something non-local in my theory at 1 meter. Naively, one might think that. But no, string theory is local. These two loops interact only when they actually cross. And everything happens at that vertex where they cross, right? So it's just like cosmic strings. Where they can cut and rejoin. But the rest of the string doesn't even know that something has happened till the signal reaches all the way there. So in that sense, string theory, even though it has extended objects, and you can stretch a brain or a string to be as big as you want in principle, it does not mean that anybody has got signals to propagate outside the light cone in string theory. Okay, so I mean, that would have been very big news. If you can send information outside the light cone in string theory, you would see it in the New York Times. But the string theory is completely causal. And what we mean here by the size of the object becoming big is the same sense in which if you take a string and you put a lot of energy in it, the size of the string grows. If you had a point particle, you put more energy, it can just run faster, but it can't grow. But if you put more energy in a string, it can stretch. And so what basically we are finding is that when you make bound states of multiple kinds of branes, the ones which give you like the Schrödinger one for black hole or any black hole, you take D1 branes, D5 branes, all these kinds of branes, they make bound states, which if you put a lot of branes in there, the bound state doesn't want to be small. Its natural dynamics makes it grow in size. And so that's what is happening. The bound states in any theory have a natural size. Like in nuclear physics, the size of a bound state grows with the number of atoms to the power 1/3 because it's hard sphere packing. Nucleons pack hard sphere to give you nuclei. Okay, so some other theory like a BEC, all the bosons sit on top of each other. The size of the bound state doesn't grow with the number of bosons. Right? So every theory has its own growth of the size of a bound state with the number of quanta in it. That doesn't mean the theory is non-local. So the theory remains completely local, but the size of the bound state can still grow with the number of quanta. And I think I just wrote that here because normally people always assume that because the only length scale coming out of C, H bar, and G is Planck length, the black hole has to have this picture. Any quantum gravity will happen here, and all this must be semi-classical. But that's not true. Once you have an N in the picture, dimensional arguments don't force that. But of course, then you have to look at the theory. And if you have just ordinary canonically quantized gravity, you will still get only LP. There's no way you can get this. But because these extra dimensions can twist and turn and branes wrap them, flux, all the stuff we get in string theory, then definitely this is what you actually end up with. So that's a calculation. Each structure you try to make, you actually get this structure. But if you want to look at the structure, it's just something like what you get in gravity, some bubble of nothing here, Euclidean Schwarzschild here, join them by a flux somewhere. It's just local constructions.
One short question. If you put large number of string states in some volume, will there be some asymptotic freedom like it is in QCD, for example? I mean, the interaction,
I don't think so.
Yeah.
So I don't think so. I mean, gravity always goes the other way, right? Gravity gets strong when you go to more energies. And you'll just enter the black hole domain. So if you go to high energies, instead of becoming asymptotically free, the cross-section at high energy impact, instead of becoming free and guys going through, you basically end up saying that the cross-section grows like the area of the black hole you will make with that much mass. Mm-hmm. So, there are estimates of Billings and so on, to try to give that some more flesh on this argument. But the cross-section grows like the Schwarzschild radius of for that much energy, I think is pretty well accepted. So it's the opposite of asymptotic freedom. Okay,
this I agree. Well, some people consider quantum gravity not asymptotic freedom, but asymptotic safety is also one criteria for quantum gravity. Some is different community working on it, and just want to know your opinion on this.
Opinion on what? I didn't catch the question.
Asymptotic safety. So okay,
asymptotic safety. Okay.
Yeah.
Yeah, I have read some papers about asymptotic safety in gravity. I don't actually remember right now what exactly they said. So maybe we can talk offline. I'll have to see what the claim was to make a sensible answer. Yeah.
Okay. Thank you.
Okay. Next question from Raifah Khan, please.
Hi, thanks for the nice talk. I have a question about Hilbert space factorization. People usually say, like in those nice slices, when there's gravity present, the Hilbert space does not factorize. I would like to know what are your thoughts on that.
So yeah, so I think that those arguments are not right. If you have a completely smooth slice, nothing bad anywhere, like a slice through the galaxy or through the universe, or even a good slice through the black hole, people keep making these arguments that degrees of freedom in one place are somehow not the same as degrees of freedom. I mean, are the same as degrees of freedom somewhere far away. I have never seen any evidence for that. I mean, in gently curved space, we can do calculations wise, quantum fields on curved space, that remains completely local. Bits here are not bits there. And or you can do string theory, and all the string theory calculations we do, like you can have d branes, scattered d branes, but a d brane is here, another d brane a mile away. They just do locally whatever they were going to do. I've never seen a situation where the degrees of freedom in one place massively non-factorized with degrees of freedom in a different place. Of course, when you take some interval and you cut it somewhere, there'll always be some entanglement across, right? I mean, so you can't factorize across a sharp boundary, but there's just some Planck scale entanglement. But if you say something here is inside the black hole is the same as bits far away, I have read those arguments and they never made sense to me.
What my understanding is that in the context of holography, like as the degrees of freedom in the bulk are encoded in the boundary. So like in those slice which goes inside the black hole, the part of the slice which is inside the black hole, like on the hidden surface, the degrees of freedom on that could be encoded in the degrees of freedom of the late Hawking radiation, which is far away from the black hole, in the same sense as holography, right?
So I know that people say that, so I'm glad you asked about it. But I think what they are doing is they are making a couple of jumps, which I think are wrong. So I think that's what I was saying. People have drawn lessons from holography or ADS-CFT, as I was saying at the end of my talk, which are just wrong. And I think that's why these mistakes are happening. So like, here's a picture of ADS-CFT, right? The entanglement is between so the area is in the bulk, the entanglement is in the boundary. Okay, so let's just be very clear about that. The bulk, it's the same theory. You describe this in terms of open strings, Yang-Mills. The open strings, if you look at the closed string channel, it gives the gravity, which is the ADS. This theory is just different variables on this theory, right? And then in this description, what shows up as an area, in this language shows up as an entanglement. Now come back to what people are trying to do here. People are trying to jump to a situation where everything is gravity. There's no dual CFT, nothing. This is a gravitational region, this is a gravitational region. Gravity will be strong or weak, but it's all just one theory, like our universe. And entanglement here to here is giving you some kind of a physical connection or some kind of rules or some lessons. There's no connection between two things in the same theory, the gravity theory we live in, but some region here in my room and some region there in Moscow. But which are not connected by any Hamiltonian. There's nothing you can say about this situation, which is like this kind of situation, by what you're looking here. Here, everything is connected to everything, but they're all in the ADS. There's a Hamiltonian from point to point. It's the Hamiltonians which are important, not the entanglement. Here, this is the dual description. Again, there are Hamiltonians here. And that's what I was trying to say. People have turned this around, and that's a big mistake. Hamiltonians give entanglement. Right? Hamiltonians generate entanglement. Entanglements don't generate Hamiltonians. So when they turned this around, they made a very serious mistake. They were looking at ADS-CFT. They saw from this that they're getting some entanglements, but the source of these entanglements were the fact that the harmonic oscillator here and the harmonic oscillator here were coupled because the bits at neighboring points are coupled in the angles. That led to the fact that the ground state will be entangled. That's how entanglement comes in any field theory, in any crystal, in anything. It doesn't mean that if two things are very far away and they are entangled, there has to be any kind of Hamiltonian or effective space-time wormhole between them or anything. So because they turned it around, I think everything from that point onwards is wrong. So if you try to actually make a rigorous jump between what you saw in the RT and coming to what they are saying in terms of these wormholes or non-local identification of bits, you find that the steps don't work. And so certainly if you want to make that argument slowly and carefully, step by step, I'll be happy to sit with you and see how you go. But I'm claiming you can't go.
Okay. Thank you. I have another question regarding this. I have a follow-up question on something that you said in response to someone that asked about that dual wormhole. And that I think you said that the information inside that eternal black hole should eventually come out from either one of the side, right?
Yes.
What stops me from saying that it will actually not come out and it can go get destroyed in the singularity?
No, nothing stops black holes. No, you can say that. I'm just right now using the fact which these people all want to claim, because everybody who was doing this game also wants at the back of their mind that the information really comes out. They want the page curve to come down. If you want to put it in the singularity, you have, as Robert Brandenburg was saying, you have a remnant scenario. You want to stay with that, that's fine. If you want the page curve to come down, then the information has to come out. And all I was saying was, once you have a physical connection between them, once things reach the forward wedge, it's impossible to separate what came from the left, what came from the right. Anything coming from here crosses the halfway point quickly within crossing time, and it's here. From here, it crosses here. They can interact and produce something. It's impossible to separate things that reach the forward wedge into what should come out here and what should come out here. That's what I was saying. If you want to say the information doesn't come out, then it already doesn't match with this, because here it's the CFT with a bounded number of states. If you throw something here, because not more than S-pack states can be there, you throw too much stuff, that information has to come out. Then it already wouldn't match with the CFT. So these guys match it to the CFT. They believe in the CFT. They don't worry about how it comes out here, but they just say, somehow it comes out. Using that, I have shown a contradiction. But I think it's this picture, because here it comes out here, and it also comes out here. It just bounces and comes out with some mess up, right? So you have to be consistent about the information. If you say it doesn't come out, I think there's inconsistency one step before that.
My understanding was that information should come out only if the black hole is decreasing in its size, but it need not come out if the black hole is eternal.
Okay, so we have to be careful about what the word eternal black hole means. So eternal doesn't mean that the black hole doesn't radiate. So eternal means the black hole is radiating, and you're also feeding it at the same rate at which it is radiating, because once you have a smooth horizon, you can't stop the pair creation. So the whole point is that if you do that, okay, don't let it evaporate completely, but if you keep feeding it and letting it evaporate, after you have done this with more than S-Beck times, the stuff has to come out, because otherwise this entanglement will become more than S-Beck. So if you want to match this side, and you don't want the entanglement to become more than S-Beck, it has to come out, and it will come out through both horizons. So that's the kind of arguments I use here. So I also talk about non-evaporating hole in this paper. So yeah, you can take a look at that. Same problem.
And if you have to say, for some reason, if the information does come out only from to the side in which it previously was in, then we have to give an argument of why that would be the case.
Absolutely, that's all I'm saying.
Yeah.
Somebody can say that, but it makes no logical sense to me. So
yeah, okay.
That's all I'm saying. Yeah.
Okay, thank you.
Okay. The next questions from Shao.
Oh yeah, so I just have a short clarification question. So it seems like the work by Marov and Maxfield that you mentioned, is going in a different direction than the island proposal due to the non-unitary evolution. Is my understanding correct?
Okay, so let me put it this way. In principle, from outside, it appears that all these proposals with the island and Marov-Maxfield and all these proposals are trying to do the same thing. So they will say that they are all doing the same thing. But when you go to look at what they are actually doing, I find differences. So that's why I talked about ABC, the different things. And so when you actually go to dig into what is happening, in each of those, you will find a different problem. So in some of them, you'll be forced to non-locality, like some bits here are identified with bits there. In other cases, you will find non-unitarity here. Sometimes you'll find a Euclidean argument, so the states you want to look at are not even there. So each one has a different problem. So that's why I talked about 3 different cases, but they were all trying to argue for the same thing, that you can have a smooth horizon and you can still get the page curve to come down. And they never talked very clearly about whether they have or don't have non-locality. So because that is never talked about very explicitly, what I've done in this talk is I've tried to lay down what you can and what you can't do. If you don't have non-locality, you have a smooth horizon, you have to have non-unitarity inside. If you look at the Marov-Maxfield paper, that's not what it says in there. So that's why I'm not saying that that's what the Marov-Maxfield paper says. They just make this new dot product. What I'm saying is that that implies this. It either implies this or you have to have the non-local interaction. So I'm saying that I'm not quoting Marov-Maxfield when I'm saying it's non-unitary. That's my concern about it. So I was giving you my concerns about these papers. These papers somehow on the surface all seem to say that somehow by using JT gravity and replica wormholes and new topologies, I can get the page curve to come down. It just can't be true, because this 2D gravity has no more power than the 2D gravity in CGHS time, and you can break this thing, you can allow new topologies. It doesn't get you any information out that we knew all along. You can always have broken it off into a baby. That doesn't get it out. The baby universe is a remnant. If you want a remnant scenario, you can always have it, right? But these guys are wanting the page curve to come down. We have known for years that that can't come down. So what is the new thing that they are doing which can make it come down? And I'm just arguing, actually, there is not a new thing. The page curve doesn't actually come down. It's either the old thing like non-unitarity, or it's the new non-local effects, or it's actually a remnant scenario. All these things can be found in different papers. Some are actually saying it's secretly a remnant. Some are actually saying it's non-unitarity, but they don't actually say it in those words, but they're not what is equal to that. Or they might be saying it's non-locality, but again, they don't make it explicit. But those are really your choices.
Thank you. Thank you.
Okay. The next question from Luca Smarden. Luca, please.
Okay. Thank you very much. Very, very nice talk. I just want to know your opinion about another possibility I see to overcome this kind of difficulties you see. If you have a theory which has natural ultraviolet cutoff, you can think, for example, to word crystal description, for example. In that case, if you consider a finite volume region, you have just finite number of degrees of freedom available. So in that case, in a certain sense, you have no problem from the very beginning, and you don't need fuzzballs, and you don't need non-unitarity or remnants and so on.
No, that's a very good point. And I think that it's something I've thought about many times. And let me tell you what I find so interesting about. So I'm going to say, somehow we know that can't be true. So let me just rephrase your question this way. Suppose you have space-time, and we say that Planck length is a cutoff. So there is nothing below a Planck length. So there are Planck length number of bits in space-time, and that's it. Okay, very good. Then let's ask, how does our universe expand? So suppose you take a flat universe, and let's put it on a torus just to make it finite so I can talk about it. So suppose right now, in terms of Planck units, it has 1 million cells. So there are 1 million bits. A Hilbert space has dimension 1 million. And then the universe expands. And now it has, because Planck length is the same, it has more cells, right? Now, how can you have something whose dimension of Hilbert space was, let's say, 1 million, and then it became 2 million? I cannot write a Hamiltonian theory with the size of the Hilbert space is changing, right? So somehow anything we do, we always assume there's a unitarity, assumes there's a Hilbert space on which I can act. If the Hilbert space wasn't infinite dimensional at all times, then I can't even do this. So how the universe expands is then that would become the mystery. And that's why I think the crystal idea doesn't work. Because if you look at the inflation, the universe starts the size of a marble, 1 centimeter, and today it is 3000 megaparsecs. So we know that space can just keep expanding and expanding, and that just doesn't create any problems. Like it was just a few Planck lengths at that time at 1 centimeter, not few, but 10 to the 43, and now it's 10 to the 30 times bigger. So new degrees of freedom seem to just come out from somewhere, and it is something we really need to understand, right? Because a naive model would be that Planck length is a cutoff, and that's the atomic structure. That's the first thing anybody would like to think. But we already know that it's not compatible with an expanding universe. So I think it's a very interesting thing to think about. But I think it's not true that there is a crystal model.
Oh, thank you very much. Very interesting point to think about.
Okay. The next question's from Anupam. Are you here?
Hi, Samir.
Hi.
Okay, very nice. So one of your slides, I think you mentioned about this entanglement, that if the two states are entangled, then it doesn't necessarily mean that there is an interaction.
Yeah.
Now, yeah, so now the question is, suppose, yeah, exactly, this last bit.
Yeah.
Now let's say that these 2 bits are within your causal patch, and there's nothing else, there's no other physics. Let's assume that. Then there exists a very nice theorem, which is, you know, perhaps LOCC, which says that local operation and classical communication, and in quantum information, that if you have local operation and classical communication, then you cannot entangle.
Oh, yes. Okay, that's true.
So suppose I have got this Alice and Bob, and I assume that there is nothing else, and if they are entangled, then the question comes that what leads to their entanglement?
Okay, so that's completely a valid question to ask. So the way I imagined what I had drawn here was the fact that at some time in the past, these 2 bits were together, they got entangled, and then I sent one here and I sent one there. Absolutely, that's exactly what I meant, right? So they are in the same causal wedge of everything, like that. They actually came out like this, right? The question is that now that they are far away, there is no Hamiltonian between them. So now the question is, if I measure this by a Stern-Gerlach experiment, what happens is just what we normally get in the lab in terms of quantum mechanics and entanglement. There's no Hamiltonian interaction. But that's exactly what happens in the black hole. In the black hole, we created an entangled pair at the horizon. One guy stayed in the black hole region and one guy went out. So we did send them out like this. We did create them together and send them out exactly the way you're saying. That's the only way I can entangle them and then create them. And the problem then is the entanglement of the guy which has gone with the guy which is here, that is growing. So the whole problem comes because the black hole, because the states in there have negative energy, the whole black hole then tries to vanish, because even though there's a lot of stuff in it, the total energy is going to zero because the negative energy quanta in there. And so at some point you say there's nothing here, so I'm entangled, but how am I entangled with somebody? So the troubles then come at that level. But at all times when we are creating entanglement, we are doing it exactly the way you're saying. At some point, local bits are entangling and then they are moving up. So that's the thing which I was showing in the beginning. You have a big cloud of mess and then something gets entangled, comes out. You don't even have to know how it happened. It all happened in one region. And then it moves out. Absolutely. If they are far away, I can't entangle them.
Oh, thanks.
Okay. I guess the last question from Vedeon. Vos, please.
Hi. Sorry, you've probably already covered this. possibly when you answered someone else's question and you mentioned once you mix milk and water, that it's very difficult to separate them. It's a nice expression. I like that. I remember a couple of years ago, there was this work by Aaron Wohl and collaborators on the traversable wormholes, where if you conspire some initial conditions, you could send in some negative energy shockwave into a black hole to make the black hole shrink on the other side a little bit and make the an observer to just cross the horizon and come out again. So how is this, what would you say is the counter argument? Is it just the initial assumption that they were entangled in the first place?
Yeah, so I think as I try to list that as one of the two possibilities, right? So I think whatever they are saying is then equivalent to this. You create this entangled pair, and then more and more guys are collecting inside. That's what's leading to the growing entanglement. And we want to say we can't entangle by more than S Bekenstein, so something has to get out of here. But suppose the entangled partner here travels out through some wormhole and reaches infinity. Then you can keep saying that there's like an escalator. You know, more pairs are created, but then the same guys come out. And then if this guy comes out, then this guy's entangled with this and not with something inside, so you're okay. So I think in the end, the whole wormhole paradigm has to either end up here. That's what I'm trying to summarize here. This was my last slide, actually. You either have non-unitarity inside, which people are not recognizing, but that's what's happening in the Marov-Max field kind of thing, because they don't talk about these non-local effects. So then they have to have here. Or if you really want unitarity inside, then you can have this escalator where something from here really comes out. But it's not that you have to make something to make it come out, unless it comes out automatically, like the wormhole creates automatically and comes out, you still have the problem, right? Because you collect more than S Bekenstein over there. So if somebody says that there is some magic by which these wormholes are being created, and once too many things collect here, the wormhole pops out, goes all the way out to infinity, and then sends things out, it's fine. You can make that model. Absolutely, you can make that model. I'm just saying there's nothing in string theory which makes me think that's correct. But that is consistent, at least with unitarity.
Okay, excellent. Thank you.
Okay, there is still one more question from Christopher Marek, please.
Yes, I have just, I'm not working in this field, so that's maybe a naive question. But what is the, let's say, problem with the fuzzball picture, which makes other people try to look for the solution of the problem using, let's say, other ideas? I mean, from what you said, it looks that the fuzzball picture is just the accepted solution of string theory in some particular setup, but still others who are string theorists are looking for another solution of the problem. So what's the kind of, I mean, so yeah, so that's it.
No, I think I understand the question. No, it's a very important question. It's a very, very critical question to ask, because exactly as you say, I give colloquiums on this information paradox. And after I tell people, look, this is what we are finding, and the small correction theorem tells you, you need an order 1 correction. We actually make the string states and we find the order 1 correction. There's no horizon, it's completely corrected there, right? They say, okay, why is anybody asking a question? So everybody who doesn't work in string theory always says, why is anybody saying the problem is not over? And I think it is over. I think, as I was saying just a few slides before this, the whole problem has been created because of a wrong belief in the lesson we should draw from ADS-CFT. That's the whole problem. Because people thought that because of ADS-CFT, a messy thing could have an equivalent description as something smooth. So Juan and others kept looking for some description of the fuzzball, the region near the horizon, where they say, okay, you may have a fuzzball in some language, or maybe you don't have a fuzzball in some language, but somehow effectively the black hole should look smooth, at least in some description near the horizon. So that belief, I think, ultimately came from what they deduced from what they had seen in the ADS-CFT case. That's only my guess, because I'm trying to give reasons for why somebody may think something. So obviously I can be wrong. So then people may start thinking that whatever quantum gravity mess is going on here, you can think of this like a fuzzball. It must have some simple description also. But the point is, as I was saying, once you have any entropy, if you have no entropy, that's possible. But once you have a surface whose inside has a huge entropy, then all these states are different, and you cannot replace it in any approximation by a smooth geometry. And then we have this explicit case I was showing you, that in the Twocharge case, we can actually see that in the region where the entropy is, that region is given by the horizon size, where the horizon scale. And there, in fact, you cannot replace them by one common geometry. So you can see that you can't do that. But this is the mistake. People are trying to replace it by one geometry because of this intuition. And so I think the ADS-CFT is a very useful tool. But in the end, it's just a change of language, right? Open strings to closed strings, just a very complicated map of variables. But I think if the lesson from that is taken in the, is a lesson from that you draw is not the correct lesson, then you can get into this mess. And I think the information puzzle has been over for a long time. We know the fuzzballs, that's what we need from the small correction theorem. But for a long time, people were thinking that they could keep the smooth one. So they have the semi-classical approximation, then they'll put small corrections in it and somehow encode the information. So that was going on till fairly recently. And the small correction theorem was only in 2009. But after that, people were still worried about this. But that I think is because they're still trying to force the ADS-CFT intuition in some way. But I think once you put the small correction theorem along with what we have learned from the fuzzballs, that's why I drew them both on the same slide, the small correction theorem in the middle here, that really takes care of everything else. And you have all the limiting cases, you can have like neutral black hole, which is fast rotating, or extremal and over rotating, all different cases you can cover. But anything in the middle is not extremal, it always radiates. Once it radiates, the small correction theorem captures it. So I think it's over.
Okay, thank you.
Okay. We still, one more question. A question from, I'm not sure that I pronounce it correctly, your name, Shenriar?
Almost. Sheriar.
Sheriar, okay, thank you.
And sorry for the late question as well, but since the diagram right at the end is there, I thought I would just ask. Professor Mathur, you at some point you gave the formula, I think you called it the Strominger-Waffa formula, where RH was given by basically square root of n1, n2, p alpha, well, whatever the formula was. But it corresponded in this picture to the configuration right at the top left.
Yes, that's the generic state. That's the generic one I've brought here.
Right. And if so is there a similar formula for all the other configurations or edges of this diagram?
Okay, so let me see if I understand the question. Maybe you're referring to the formula where I gave an estimate of the size.
Right. Is
that what you're talking about? Yeah.
Yes,
so Strominger-Waffa, yeah, go ahead. What's the question?
So your, it was size and RH. I think that's the horizon area.
Yeah. So that was an estimate I made way back in 97, just 1 year after Strominger-Waffa's very nice paper in 96. So Strominger-Waffa just took these microstates. They did not even have these things going both ways. They only had D1, D5, P, but no P bar. Then later people did the P bar, that's the current models in the near extremal. But anything extremal or near extremal, in terms of branes, is made of 5 branes which are in green, 1 branes which are in red, and momentum, maybe anti-momentum if you like, which are in these blue vibrations. So those are all the states. And then if you want to estimate the size of the generic state, it's given by that formula. The non-generic states, there's nothing like a size. A non-generic state could be very big this way, very big that way. It could be anything odd, right? It could be of any size or any shape. So these are very non-generic states because you make something where, but here in cases where you can make all the states, the two-charge case where you don't put any momentum, just have D1 and D5 branes. Here you can make all the states in closed form. You can see their size, and the generic size is such that the area bounding them satisfies A over G is of the order of the entropy. So you can see how the Beckstein relation is coming out, that inside some region where it's all messy, you can see all the states, and the bounding area satisfies the Beckstein relation, and you can see there are no more states you can fit in there, because more than that orthogonal states don't fit in that region. Since you have them all there, you can just see that happening. So in very simple cases, we understand everything. All the fuzzballs are known for this case, inside out. And then when you go to the third charge, you know various different limits. And I think the limits capture basically everything that you would like to capture. So it's not like there's some direction where you don't know what's happening, but you don't try to estimate the size of these guys, only for this case where you can do all states, so you can do generic. These are non-generic. You look at some extreme cases, so their size will not have to match that formula. But the generic one for which you do an estimate, that matches the size formula.
All right, cool. Great. And so just to confirm, this is type 2b compactified on K3 cross.
You can do type 2b on K3 cross S1 or T4 cross S1. Most often we work in T4 cross S1 because the dualities are easier, but you could do K3 cross S1.
Cool. And the space-time is ADS3 or?
So the
can you-
space-time, the naive geometry would have been ADS3.
Right.
So if you take the simplest case where all these circles are single and there's no momentum on it and their spins are all aligned, that geometry is ADS3. So ADS3 is just a special case. You have flat space
That's a very
going here, giving ADS3, but then all these other cases are the other states. The ADS3 is the NS vacuum. But these are all the other states.
And can you say what the geometry is in the other cases?
Yeah, so that's the whole point, right? We make the geometries for all these cases. So like here, when I say we make all Twocharge extremal, I'm not just writing these states down. These states are just telling you which state this is. But the fact I wrote it in the diagram means we actually made the geometry for all of these. That's exactly what's being said here, right? So like these geometries, these are Twocharge geometries. We actually make these structures which show you for each of those states in the CFT, what is the actual gravity solution.
Mm-hmm. So wait, let me just get this right. Okay, so I see. The only change in the geometry is just basically the area of the horizon.
No,
the geometry in itself is still ADS.
Delta meaning?
No, the geometry itself is still ADS.
No, it's not.
The
geometry
area
here
of
is not.
So this entire thing is red line, and S micro basically says what the area of the boundary would be.
Okay, so let me just say what this picture was saying, because I went to it quickly because it was part of something else. So the geometry created by any one of the D1, D5 microstates, which you can count in the CFT one by one and list them out, is flat space far away because the brains are sitting somewhere in flat space. So far away, it has to be flat space. Then there's a region which looks like ADS3 cross S3.
Yeah.
And then, but when you get towards the bottom of ADS3, they all have very complicated structures, which is not ADS3.
Yeah, okay.
And each one has a different structure. And the order of size of the region where they start differing, if you take the boundary of this area, it satisfies the Becker-Stern relation. So you can say the states all differ in a region of that size, but none of them have a horizon. In this region, the metric is not ADS3. It is what it is. It's different for every state. And the boundary area for the region where they all differ satisfies the Becker-Stern relation. So this is what my understanding of the whole complete solution of the black hole puzzle is. Far away, they look the same, like a black hole. But once you get to the horizon and inside that, they all start differing. In this very simple case of Twocharge extremal, we have all the states. We know there are no other states. We can count them all. We have counted them in the gravity, in the CFT. They both give the same answer. We can semi-classically quantize them. Everything about them is known. And there's no mystery. There's no horizon. There's no singularity. Any metric you want for any microstate, I'll give you its geometry.
Wait, okay, that was the question. I mean, it was your answer was basically in it is what it is, and it is known explicitly. Like you can actually give the metric.
For the Twocharge extremal, they are all known explicitly, and for the more general ones, for all these cases, it is known. You can't make every case because it's just more messy, but that way you never make every planet, right? If you want to say planets don't have a black hole puzzle, you'll take simple cases like a uniform crystal or a thermal gas. Anything else, you'll say, okay, it's something. So it's like that kind of limits, all the limits we can make, and then the rest is something. But if you had a horizon there, then the small correction theorem catches. So I don't think there's anything to worry about there.
Okay, so there is no more questions, but in any case, we have a lot of discussion. Let's thank the speaker again. So we have a very nice talk. We have a lot of discussion. Thank you very much. Thank you very much for all for joining us.
Well, thank you very much. I really enjoyed the discussion and the forum. Very nice.
Oh, thank you. Thank you.
Thank you very much.
Thank you.
Thank you.
Okay, so next 2 weeks will be a string conference, so we will meet in 3 weeks, I guess. Okay. Bye-bye.
Yeah, 8th of July.
Yes, 8th of July. Yes.
Okay.
Okay.
Thanks to everyone.
See you, Samir. Thank you very much.
Bye.
Bye-bye, everyone.
Bye-bye. Sign off now.
Okay.